Um, it's I saw the write-up that accompanied this, that came along with the brochure, and it says lots of wonderful things about him. I would like to add a little bit more. I mean, about Kapil and also my personal experiences with him. Um, yeah, so in addition to what was written up there, from talking to people in math science, especially V.S. Sundar, told me how much work Kapil did, because he's such a nice person who can never say no, taking care of the computer responsibilities, the administrative systems, and I think took a lot of time away from his mathematics. But he's like that. He's just eager to help everybody out and naturally interested in so many different things. Um, and one one particular thing about Kapil stands out for me. I mean, learning something new is not a simple process, and it takes time. And Kapil is, I think, extraordinary in the sense that when he sees a new concept, he internalizes it. It fits so well in his frame, in his picture of mathematics, and it's uh, at any level. And it's wonderful that he and Sudeshna decided at some point, 15 years back, roughly, to take it to go like full time into teaching or teaching undergraduates. And I'm sure lots of people would have um profited from his lectures, the clarity of his vision, discussions with Kapil. I think it's really a great service that is done. And then, of course, speaking personally, that is for myself, well, I've had plenty of discussion with Kapil over the years, and it's been wonderful to discuss mathematics and learn from him occasionally, and also from his peers like Srinivas and Deependra over here. We are living in, and a superb time right now where problems that Kapil, myself, many of us have been very interested. Uh, there's been solid progress in the recent past, and I'm talking about A.L. Markman, who uh, took care of the wave classes, took care in the sense that proved the Hodge conjecture for them by representing them by algebraic cycles. In dimension 2, extending Chayat Shahin, who uh, a paper that Kapil almost started out with. And when I found that Malkman had put his paper on the archive, I was very tempted to say, I'm going to spend, that was on February 5th, I think, or 6th. Let's spend all our time reading it and try to say something about it here. Unfortunately, I didn't do that. And I just thought I'll report on work that I've been doing with Deepam Patel. It's been going on for quite a while. And one part of it has got published, not published, written as an achievement. Yeah. So let me just say a bit about what's going on here. Uh, yeah, so I think I'm starting talk here. So the we're all, of course, everything starts with Grothendieck. And if I've got a variety X, uh, say, defined over complex numbers, we had HQ of the complex topology, which people often write and, but I'll skip writing all such things when the context is clear. We have these integral cohomology groups which you can complexify, etc. And there were new structures found on them, thanks to Grothendieck and various comparison theorems. Yeah, so this is, you can now see why I decided to write down part of my talk before. There's there's ethyl cohomology, and there is algebraic Durham cohomology. And there are various conjectures with regard to motors and what all this is supposed to do, which we'll not go into right now. Uh, but as I wrote, the main thing that we were looking at that was to talk about abelian covers, a family of abelian covers. For instance, you could start with a variety and take a rational function and take nth roots of it. You can take a map to an abelian variety or a semi-abelian variety and take a fiber product with an n-fold covering. And right. And so we get cohomology groups of new varieties. And there were two things that we were aiming at. One is to write down, I didn't mention hot structure, I forgot. Among the various things, it's classically the most important one. And this is, of course, Boolean. I mean, mixed hot structure, which are not necessarily working with predictive varieties. Yeah. Boolean, of course, as everybody knows. But we didn't quite make enough progress with this, not some, but so we wanted to do this thing that is, what are the counterparts of that and that? What are the comparison theorems in this context for these coverings? Try to, yeah. And then we also sort of made a category out of it. I don't, I don't know whether that will ever get written up. That turned out to be more complicated than just for varieties defined over some subfield of the complex numbers. Okay, so that is by sort of way of introduction. Okay, so whether the choice between taking abelian varieties, semi-abelian, and or just Storai. So yeah, so I've got a variety over complex numbers, and you can get some slight improvement if you assume that it's defined over a subfield of the complex numbers. And these are F1, F2, Fn are just function. I mean, functions from X, not just rational function, but morphisms. Each one is a morphism, not just to the affine line, but to GM. And so I use F for this n tuple. I have that. And you can adjoin the rth roots of all these things here. Adjoining, which means in reality you're taking a fiber product. I hope my notation, I hope it's legible. F of x is equal to z raised to r, which is fi of x is equal to zi raised to r for each I. And then one can attempt to compute the cohomologies of these things. So you're getting ethyl covers, finite ethyl covers, Galois covers of these of your original variety X. You can ask what its Q cohomology looks like. Of course, as in the case of cyclic covers, we see like union constructing Fermat hypersurfaces and so on. There is the Galois group, which is, of course, the roots of unity operating on each of those coordinates. Yeah. So we have the rth roots of unity times cross itself n times that operates. And if you're working with rational cohomology or this invert R, this cohomology group that one is concerned with would break up as the direct sum of the cohomologies of each of those rank 1 local systems on X. So these rank 1 local systems are essentially got by, I somehow it's not written here, but it's written on the next page. Anyway, one can say one is just adjoining, yeah. So on X, yeah, on X, if I fix rational numbers whose denominators, yeah, things like, yeah, denominators are divisible by R, and if I call them, say, S1, S2, Sn are rational numbers, such that R times the SIs are integers, then I can take Fi raised to Si and adjoin them to X, by which I mean precisely I'm just taking, uh, that gives rise to a rank 1 local system on X, and I can take its singular cohomology. And then this would be the direct sum of all those things. And in such a situation, there is a standard thing one could do is, why not work with a universal local system and get all these from the universal one and do a universal coefficient theorem to derive one cohomology from the other. Universal coefficient theorem, which people like to call left derived. So the universal one would be, it's to take the group ring of the fundamental group of the torus. So this is just integers cross itself n times. This is C star cross C star cross C star a bunch of times. And yeah, it's a commutative group. And so the group ring is just a Laurent polynomial ring in n variables, right? And there is a natural local system, uh, which I'm denoting by a script L here, whose stops at a point Z on the torus. Z is a Z1, Z2, Zn. Is just taking all paths in the torus that take 1 to that. And that is a torsor, because you get torsor under paths loops at 1. And so if I take the free abelian group on this set here, which I denote by LZ, I get a module over this Laurent polynomial ring, which is got by taking this point also to be the identity of the group. And of course, it's free of rank 1. So I remember telling this, and Srinivas remarked, and I'm going to repeat his remark here, because it's good to be able to see things in as many ways as possible. He was saying, if you want to construct a local system on a space, all you need is a homomorphism, a local system whose stalks are, say, an abelian group A. All you need is the homomorphism from pi 1 of your space to automorphisms of A. And there is a natural homomorphism from any group to it, the automorphisms of the group ring, simply multiplying by units, since the group itself sits inside the group ring by units. So, of course, both procedures give rise to the same thing. So whichever way one wants to look at it, it's fine. Okay, so that gives you this, that's the stock, and that gives rise to this local system on the torus, It's a local system of R modules free of rank 1, as I just said. But we started with a morphism from X to the torus, so we can pull it back and get uh, a local system on X. Now, whenever you've got a homomorphism or yes, and so we can do a tensor product. If I'm given a homomorphism from the group, in this case, the group is V raised to n to C, C star, excuse me, that gives rise to this homomorphism here. And so you get this system L chi on T. And whatever one wrote on the previous page was a special case of this where chi was going into the R roots of unity. Right? That's right. So computing the cohomologies of this on X and using a universal coefficient theorem would also get you the cohomologies of that. And so we have this here, which is this is just notation here. If I'm taking cube cohomology, collaborator Deepam never likes to write that, and you go straight to the derived category. And as I said, yeah, I already said that it can be, we can recover the things that we are primarily interested in by a left derived functor. Okay, so whatever this thing is, and I haven't written anything here, but I'll do that. So back to this, I want to compute this, or at least make some elementary remark, which is all that is going to happen here. Now this X, it's a variety. It has the topology of a finite cell complex. So to compute the cohomology, you can just write down a cellular complex. There are only finitely many cells in each dimension. So you get a complex of R modules. It's a finite complex and each term is free. So when you take the cohomology, and R is very much a Noetherian ring, so the cohomology is going to be a finitely generated R module. That's all that has been asserted here. And now going in one of the two things, and going in the direction of algebraic geometry in the sense of convention more than anything else. If I've got a module over a commutative ring, I get m tilde, and that's on an affine scheme. I get, I get this thing on spec of R. Now, spec of R can be canonically identified with the dual torus, whose points would be the characters, homomorphisms from T to C star. And actually, all this is doing is nothing but keeping track of each of these groups, L chi, for all possible. I mean, these L chi's, just keeping track of them all at the same time. But one has to use some language just in case there may be jumps, for instance, in the cohomology groups. Okay. So that would be something like a Betty theory, which has been turned into a coherent algebraic sheaf, algebraic, on that. And from here, I'd like to go to what the corresponding Dhiram situation is. Okay, and this is a familiar thing. So I wanted to make a joke, but I thought, well, everything is being live streamed. It's not a good idea. We're talking about mathematics that is centuries old. If you think about the beta function and various other things, in fact, arise in this manner. So, right, you have an algebraic function f, but you can f raised to x makes sense, makes perfect sense locally, and formally in any case it always makes sense. And when you take the differential of f raised to s, yeah, you get that. So the f raised to s is an f1 raised to s1, f2 raised to s2, which I don't seem to have written out, but yeah. So that is short form for all that. That's the definition. And so you just differentiate it and you see this. And you can throw in a Dirac complex and yeah, bring it for a local system. And so we get that. Now for any particular value of S, if you take the cohomology of this here, right, where nabla is defined, in other words, we're thinking of uh, this as, we're just giving a name to it. We're calling it ES. And you write down this local system. Deline's book on regular singular points will tells us that the cohomology of this complex is actually the same thing as, don't seem to have been written, yeah, for all S in Cn is HQX. Should I just call it C chi? Uh, this is an X and that is a chi. Though actually, strictly speaking, it's too late to change notation. We always wrote it down this way. But in reality, it is the local system corresponding to f raised to minus s, because the sheaf is going to be uh, multiples of es whose derivative is 0. So of course, you have to multiply by f raised to minus s. Okay, so that is for an s at a time, and then for one particular point of Cn. On the
Sorry,
other hand,
Madhav, could I
sorry,
interrupt, please? Yeah.
please,
So
yeah,
chi S in some sense. Okay? I mean, it's very
I is actually, this shows, yeah, you're right. So strictly speaking, it is chi minus s. And if one had enough foresight, one would have replaced whatever one uh, wrote by replacing s by a minus s, and you'll see it entering the formulae as we go down. Yeah, but you're right. It's that character. Mhm. Right. So this is for one point at a time, but then you can do the whole thing on Cn at once too. And that's not, and as I said, you can, it's, of course, nothing, either notation, convention, no definition is going to be new. And of course, there's, with my reference, you see, of course, Bernstein. To start with, there's a very short paper by Parenson and Gates Query, which also plays with these things. And yeah, and as I go on, I'll say where the other ones come in. Yeah, here, right. Now, instead of freezing a point, you could have just worked with the coordinate ring. So there is a K just in case everything was defined over a subfield K of C, but you can ignore that. And whenever you see this, just read complex numbers for the moment. So we are working with that ring now, okay, which can be canonically identified with the Lie algebra of the dual torus. That's, we needn't bother with that at all. Hmm. So we have that, and we could use this exact same formula here. Right? Um, and so your x, which was defined over complex numbers, will now become x cross affine space in the S variables. And what was originally the de Rham complex, an algebraic de Rham complex, will now become a relative de Rham complex that is relative over the affine space. And tensor with a one-dimensional vector space, I was going to say. Yeah. And then you have the same formula for Nabla. And we could play the same game again. We could just compute its cohomology. Actually, cohomology if x's are fine. Otherwise, one would, of course, have to you say hypercohomology. Right? And since your differentials, whatever they are, if we're going relative that, they're all linear over that ring, which is good. So you, whatever you're getting is a module over it. The only change from whatever one was saying about the Betty uh, to this Biram version is that this is not finitely generated. In fact, it practically never is. Meaning, I was going to say it is if and only if something happens, but that could be a wrong statement because I never checked it. Uh, if your f maps to a point, that's fine. Then it's certainly finitely generated, but there'll be a little more coming about that. So this time we get, yeah, so we've got another module. So we are back in algebra again. Module over a ring. So a module over a ring is going to give rise to a quasi-coherent sheaf in this case. And okay, so it's a quasi-coherent sheaf. So we have two algebraic objects. One was a coherent sheaf on the dual torus, which the notation for which was a certain that, yeah. And here there is a quasi-coherent sheaf. Now, one can turn both these objects into analytic sheaves simply by tensoring with ON. And this one here, of course, taking tensor products commutes with direct limits, which is good. So I just wanted to say that this module here may not be finitely generated, but it's the direct limit of its submodules, finitely generated submodules, and each of them is giving rise to a coherent analytic sheaf. So in such a situation, of course, things could look ugly. But here, in fact, it doesn't, because these, when you take this direct limit, so now suppose I were to fix a compact subset of, of this space of C raised to N. Actually, compact set just when, yeah, it's more like a tube, but compact sets are good enough. Um, it stabilizes. So in other words, one may have started with a quasi-coherent sheaf, but, and that is quasi-coherent, but when you do a tensor with OM, when you turn it, it's still a coherent sheaf. Okay? So this is the situation somewhere it will be written, and I'm sorry it was not very well organized, some going back and forth. So, so there is was a coherent algebraic sheaf here, a coherent, quasi-coherent algebraic sheaf here, and both can be turned into analytic sheaves, and then you can pull back one and compare it with this. Why not? Right? And the theorem would be that they're naturally isomorphic to each other. Now let's make that certain clear. Uh, One should have said something here that I forgot to say. Um, yeah, this one. Now, this sheaf that you get on the S variables has a natural z raised to an action, because when you take f1 raised to s1, etc., and instead suppose you throw in an integer multiple f1 raised to m1, all that. Now that's not doing anything. That function is not equal to 1, but the corresponding nabla, etc., is isomorphic to. So what one is saying is that you have a z raised to n action, the natural z raised to n action on c raised to n, and there is an action on this module equivariant with respect to that action. And having said that, and I'll come back to this page. Yeah, I realized that this is what I should have written first. I hope it can be read. Right. So you had this thing coming from the Betty and this coming from that. And the exponential map is the map, its standard notation, of course, from a Lie algebra to that. And it says that if you pull back the thing coming from Betty, and this I is because one never threw in the negative s right at the start. The I is just replacing s by minus s. So one is doing one more pullback. Then it is naturally isomorphic to the one that was coming from the Dirac cohomology computation. It's a fairly long computation, but ultimately it just comes down to Poincare lemmas of different types. It has to be built up a bit. Uh, anyway, I don't want to say too much about that here, because as I said, part of this is written. And here there is some overlap with this paper, and as this suggests, this is 2021. So, uh, yeah, it goes into all that. And it was Deepam who told me that everything is called Alexander complex series. No doubt coming from Alexander polynomials and knots and so on. Yeah, some overlap with, and as far as method of proof goes, it's identical from a certain point of view, though, of course, all of us understand stuff for ourselves and we like to think that all is clearer. But in any case, this is the state. Now, there are some things that I have not written just because it's apart from difficulty of writing it out. Yeah. Okay. So this is actually uh, digressing, but only for a moment. That, as I said, we could consider several things, semi-abelian varieties and so on. And this was worked out by Christian Schnell. But when I say worked out, it's gone as far as it could perhaps. Uh, and with lots, I think he has a paper with Mustata and then with Peter Scholzer and Barger, but the situation there is more complicated. Uh, you don't just get a like going from a torus to a dual torus. That's not that. You don't take just the dual abelian variety, but there is a natural affine space. I was going to use the word bundle. Yeah, on that it is. And when you take the dual of an abelian variety, one is taking essentially algebraically achieved line bundles on the abelian variety which are algebraically equivalent to zero, but you can also take pairs, those line bundles with connection. And one goes naturally from one to the other. But what can occur and all, though I haven't read all these papers, I think there's still open, and it's perhaps there is a lot to be figured out in what's happening here in on abelian varieties and abelian, etc. The situation that we've been looking at is simpler, but and it's my opinion, it's not a bad idea to look at simpler things, especially when the simpler things occur more often, which is definitely the case. Mm. Okay, so all this is intimately related with D modules, and I could just say a word on that. So let me skip this page and go right here. Come back to that page later. So we worked with this here. We had a morphism from X to the torus, and if you're and we are putting back a local system from here. So I will not write it out unless somebody actually asks me to. So, we can push forward from, there is a projection formula. So you can push forward from X to T of say just Zx. I mean, you're going to get a constructible sheaf or rather complex in that category, homologically constructible on T. And then one was tensoring with the script L on T and then taking its homology. So if we chose to, we could have forgotten about the X altogether and started straight off with objects on T. And the objects would be like homologically constructible stuff. But I mean, there's really not that much difference. It only says that you may as well assume that X was locally closed inside T instead of saying we actually had a morphism, and that you already had a local system on X on this subset of T. Right? You could have started with all that. It wouldn't have made any difference to whatever was going on. But then the Riemann-Hilbert would tell you that, and with Berenson's theorem, which says that homologically constructible sheaves are no different from the derived category of regular holonomic, right? Uh, so you could work with a regular holonomic at a time, but a regular holonomic is in fact made up of the sort of things that we are talking about. I mean, in addition to taking locally closed subsets of this object, you would also have to do things that, like, looking at cohomologies of pairs. So one would be taking a closed subscheme, taking the complement, and then taking the cohomology of the pair, which is written in that with lower shrieks. So all this is to say that with some uh, notation to be thrown in, whatever was said earlier would have worked with, I won't say an arbitrary D module, or even an arbitrary holonomic D module, because it did start with a genuine geometric object. So one was already starting with regular holonomic concepts. Okay? So in any case, it comes down, we are in some form or the other, we are looking at D modules on a torus, whether or not we want to call it. So now this, of course, there can't be any originator for this particular remark that is on this page. Though I think when we were making computations, Deepan told me that this is there in a paper by Lazar and Sabah. Good to know. So just one word about D modules on this ring here. Yeah, that is the torus. We are looking at D modules on the torus. You're right. Now, here the ring is that, and normally we look at everything as an R module. But here we are in a very comfortable situation where this is a group, and you have the constant coefficient vector fields, right? They commute with each other. So therefore, we could actually look at a D module as a module over these commuting operators, which will be denoted by Si, and therefore is naturally a module over that. So this ring D contains two rings. Of course, it's differential operators on this ring, so it contains that. And then it contains that. And therefore, there is a natural map from the tensor product to this. Now, that's not a ring homomorphism, but it's an isomorphism of vector spaces at the least. Right? So given a D module over the ring R, you could, now we are switching the procedures, you automatically get a module on that affine space first, and then we've got to see what the ZI do. But then you just write down the relations and which are written down here. I mean, SI, this is a vector field and we're multiplying by a function. So this is the D bracket. So it's the derivative of that with respect to this vector field will come out, which is zero a good part of the time except that. And this identity is getting that equivariance that one mentioned, which is here. So the ZI, so V is a CS module now. The ZIs are not CS linear, but they are sort of CS linear. Multiplying by this function here is the same as multiplying by that function there before. That gives the equivariance. Yeah. Okay. And then we could try to compare holonomic and regular holonomic modules. So for holonomic, in fact, the same thing, well, one of the things happens. That is, when I take a holonomic D module and I think of it as something in S variables, yeah, it is quasi-coherent as we've noted, but it's almost coherent. That is, if you take any maximal ideal uh, and you localize, then you actually get a finite region variable. So that's the situation. And okay, so one could ask, so this is not where we were aiming at, but sort of some direct geometric constructions. So I want to just say something about what we observe. So working with these this thing here, which is that if you're looking at the locally closed variety and you can always find sub-varieties so that the relative cohomology is actually, there's just one non-vanishing factor and it's beautiful, it's free. And works therefore with any coefficient system. So if we take one of those nice pairs, the thing that we call the Betty cohomology, this would just be a free module. So we are saying there's a Zn equivariant isomorphism here in the situation that we started with. But then, to prove that something is an isomorphism may take some work, but the arrow is very concrete. The arrow is simply taking, if I take something here in the Betty, it's something coming from the round complex, and so you'll have a differential form, you're multiplying it by f raised to s. And if I want to see what's happening on the other side, I'm just integrating it on some relative homology class. And then relative homology class, that's a bounded set, compact subset, living on a compact subset. So when you write down this thing here, you'll find that the coefficients that come in, that is, in other words, the coefficients that come into this isomorphism. So I better say this a little slowly without hurrying. So yes, to start, I said I have a polycoherent sheaf here and a coherent sheaf here. Now I'm saying that this one is free. actually even before going to the end. But and therefore I could take a generator, uh, and therefore I could see what the resulting function is as a function of S. Um, and so I'll get if this is free of rank H, I'll get H functions, and these are something like relative homology classes. And just looking at them, staring at them tells you get some obvious bound. And that is what in one variable is like more or less like entire functions of order one. So take D modules D for which there is such an isomorphism with such bounds, and let's call them admissible. That is anything that satisfies this bound here. And then, we have to do this filtering because we have to take pairs and such different dimension, and then we can build it up. So if there is a short exact sequence, yeah. And if two of them have this property, then the third one should also have that property. So let's call such things admissible. So in that way, you get a collection of T values, which we call admissible. So by now, what it means is one has shown that every regular holonomic on T is in fact admissible, but we don't know about that. Is the converse true? So in other words, if one assumes bound, could one conclude that that holonomic module was regular holonomic? Is probably true, but we don't know. And there are also some other things about which part of X maps to the Torah and so on. But I think I'll skip that. Actually, I wanted to say something, and it's clearly very badly timed. Yeah, about local monodromy. There was something about what happens when the situation that we're looking at moves in a family. So this would be the data, and then we would take the fibers and look at it. And then we have Grothendieck's, again, Deepam corrected me and told me about who proved which theorem first and so on, which, of course, one should know and I should be able to reel off, but I can't. Uh, I was just going to say that there are two proofs given by Grothendieck, who shows that the eigenvalues of local monodromy around the loop. So when your base is a curve minus a finite set of points, and you'll see the local monodromy meaning around the missing or around the punctures. The eigenvalues are roots of unity. And there is a proof by Galois theory and there is a proof by using nearby cycles. The proof using Galois theory doesn't tell you which roots of unity appear, but it's a phenomenal proof which just simple but phenomenal because it just says it's in the nature of things. They simply have to be roots of unity. Going via nearby cycles does more. It doesn't also tell you exactly which roots of unity appear, but it gives you a set of roots of unity and you know it's got to be amongst them. At first glance, that's what you get. And actually, both these proofs go through in this setup. And the one with the nearby cycles is educational for me. That paper is written up and it's on Deepam's webpage. So I feel it's okay not to talk about it. So what it says is that what happens when you leave geometric monodromy. So Grothendieck, by definition, is looking at geometric local systems So suppose you take arbitrary local systems, well, let's say finite dimensional vector spaces over some field. The field doesn't have to be characteristic zero. I mean, you're taking a local system of F vector spaces. Uh, this could be a characteristic P thing. And I'm only pointing this out because there are various proofs. And the characteristic P, when it's positive characteristic for the local system, well, I mean, for instance, in characteristic zero, you could also reduce it from regular singular points instead of using nearby fibers. And yeah. But the other one seems to, at least I don't know a way of giving a simple proof. So you this time you go outside geometric local systems and you allow your local monodromy. This phrase was coined by Kashivara. Kashivara allowed the local monodromy to be roots of unity, eigenvalues. And he said that when you take the local monodromy of the local system, sorry, and he said when you do push forwards, that's still true. Push forwards obeys a curve. So essentially, that is the theorem that we prove. You, no matter what boundary monodromy you started with, you when you push forward, that is when you go to a curve, more general than that. The local eigenvalues are not necessarily the old ones, but they could be R roots of the old ones. So in principle, one would have thought, so what? This is not coming from a variety which is not saying much or not saying something interesting, excuse me. But actually, it is for our purpose because in our system, our, our local monodromy, when you write down script L, it is just the fundamental group, the elements of the torus. They are the only things that can appear. And so in the ring R, the monodromy should be something like in GLN of R, where R is the Laurent polynomial ring. And the local systems that we start with have monodromies inside the elements in pi 1, which are the monomials inside the ring. And therefore, it says in any such computation, the eigenvalues of, of this, uh, the eigenvalues on that for local monodromy are rth roots of monomials. And the point is, once you say R, I mean, there's not the same R, excuse me, I'm using the same notation for different R's. So in particular, when you go to the L chi, you will just get the images of those. So it's like a uniform way of handling this thing in many situations. And then there's also the Galois theory proof, which Srinivas pointed out was that the lemma that one proved was contained in a paper of Laura. It's like a Lang's conjecture for Torah. So I think I better stop here. Uh, thank you. Thank you for your attention. Thanks.
I think I didn't get your remark about roots of unity. What will you say?
Uh, Sorry, Kapil, I couldn't hear you. Could you shout out a bit?
So I didn't get your remark about the roots of unity appearing. So where was that? Just before this.
The roots of unity. Ah, yeah. So, right. So I said that suppose you have uh, one is looking at this, right? One is discussing local monodromy here. So I said that for the script L, The boundary monodromy is just the elements of the fundamental group, they are monomials. And by going through either nearby cycles or right, you find that the eigenvalues here, when the little s goes around a missing point of the base, uh, are roots of that. It doesn't say which rth root, or it says rth roots of that. And I'm saying that if you know the eigenvalues here, then you automatically know the eigenvalues for h upper q, uh, x as f upper star l chi. Meaning the l chi is after all given by a t1, t2, tr, tn. This can hardly be read. The chi is chi of ti, theta I. This is some root of unity, which is not. And you have a monomial, so you've got a t mu will go to theta mu in the usual multi-indexing sense. And then you're taking r theta. So it says that the eigenvalues for the system of covers that you're getting is contained within this. The mu is coming, this is the monomial. By which, I mean, I call it a monomial because it's a Laura polynomial ring, but it's an element of the fundamental group of the terms.
Madhav, I wanted to ask a question which may or may not be relevant to your talk. Can you hear me?
Yes, I can hear you. Yeah.
Um, if you are given a variety and you are given a certain unramified cover of it, let's say two-fold unramified cover,
Yes,
from what I understand, the Hodge theory of X cannot be used to create Hodge theory of X tilde.
that is right.
Is this work that you are doing is a contribution to this problem?
Nothing that I have said here contributes to that. There was
One way or the other related, even if it doesn't contribute?
no, I think one of the first things I said in the talk is that we are not going to discuss mixed Hodge structures because it's more difficult.
No, but I am looking at smooth projective variety. In fact, I am only interested in algebraic curve.
Okay,
I mean, from what I understood, there is these things called prim varieties, which Kapil knows.
that's right. So
One can understand two-fold cover from X.
I understand. Yes, I do understand what you're saying. But in some special cases, the answer is yes, you can. Not from X. Of course, you can't get it from X. But there should be a way of, like, if you're taking a square root of a function. Oops, excuse me. Let me just switch this off. Uh,
That will not follow.
but you could do it for all nth roots at the same time. I mean, you'll get some structure. To what extent it helps is, yeah, unclear.
Two-fold cover, but then one could take the, so to say, maximal two-fold cover by pulling back, get mod 2 to the power 2g, and look at that curve. But I think the Hodge theory, okay, I think I'm interested in counting points. I,
Yes.
from what I understood, one cannot count the points of extender.
Yeah, and nor was one making any such suggestion, of course, right? I mean, it's one thing to say there is a uniform procedure. I mean, there is no jump in the ranks, etc., etc. Um, but yeah, actually, yeah, maybe I should drop it and I should say, I don't know. In some cases, I know there is a structure, but to what extent the structure is really useful, I don't know.
All right.
Any more questions? If there is none, let's thank the speaker once again.
Thank you.
So we come back in half an hour.
Hi, Professor. Thank you very much for joining us today. We'll end the session over here. Thank you very much. It was an excellent talk.
Thank you.
Thank you.
Welcome everyone. So let's start the talk. So next speaker is Professor Dipendra Prasad from IIT Bombay, and the title of his talk is Some Questions on Diophantine Approximation, Real and Varieties.
All right. Thank you, Chandrakant. Pleasure to be here for this conference for Kapil Paranjape. Several decades, but it is a special occasion to come here. And when the organizers invited me, I certainly could not say no, although I feel that I am quite an outsider to the main subject of this conference. But still, it is about some algebraic varieties and some related matters, which I hope will have some interest here. Okay, so it is a topic on which I have thought about in some context about 2 decades ago, and I also wrote a paper. But in the process of preparing myself for some talks in last 1 year, I hope I have made some more progress, not in terms of proving anything, but to get a little better picture of what's involved. Somehow, I have given up on proving theorems. I am happier if I can get some points of view and some picture of the subject. So this is what I will do in this lecture to summarize a little bit of what the subject is about and what my goal is. All right. Okay, so this is a slide talk, and I am not sure how fast it will go. I hope I can keep you engaged for an hour. So there are, yeah, so these are the sections. Much of the talk is about abelian groups, commutative algebraic abelian groups. And somehow I will introduce some questions, and then we will go on to discuss. He also studied some. Okay, so here is the abstract to keep you a little oriented with what the talk is about. The talk will be about connected algebraic groups and then we look at embedding of GQ inside the QP and the reals. There is a well-known weak approximation theorem. I should have said that one is only for reductive groups, no, linear algebraic groups, which describes the closure of GQ inside GQP as well as GR. Most of the time, my topology is the usual topology on real numbers and periodic numbers. I will presume that the audience here knows both real number and periodic number, although my good friend Nitin Nisre used to challenge me that real numbers don't exist for much of mathematics. But here I presume that you will know what is QP and what is R. It is so the lecture is about the study of closure. Okay, so that is called weak approximation theorem, and that is reasonably well understood. I think the last lines say that it is precise results are not always available, but perhaps they are. But that is not the point of the lecture. Okay, so in this paper, so in this lecture, for a finitely generated subgroup L inside GQ, we will consider topological closure of L inside GQ, P, and GR. The lecture is mostly for G, a torus or an abelian variety, but eventually considers a variant of the question for semi-simple groups. That one is much more vague. I think the questions about commutative groups are quite precise. They may or may not be true, but they are very precise. Paper is written with the wishful thinking that when dealing with questions on topological closure of algebraic points in an algebraic group defined over a number field, the simplest answers hold, a well-known principle known as Occam's razor. Sorry? First page, yeah. Sorry, Kapil. Okay, first page. Yeah, but diagonal product of many primes, but I am only looking at one prime at a time. Only one. So QP and R, that's all. Yeah, yes. So indeed. So indeed, it is a question of that kind, but I don't want to dwell too much into weak approximation. That is a well-known and well-understood theory. And my aim is not to look at GQ, which is too big. Its closure is therefore easier. My purpose is to look at small subgroups of GQ and still want to have something nice. The purpose is not to look at GQ, which is quite large, or which may be large. Okay. So just to give you some introduction to the subject of Diophantine approximation. In fact, this is in a certain sense a representative theorem due to Kronecker, that if you take a real number theta and consider it as an element of the circle, then it generates a dense subgroup if and only if theta is irrational. So this is kind of motivating theorem for the talk. This theorem has many refinements already in one variable of great significance, such as the following theorem due to Dirichlet, a well-known consequence of the pigeonhole principle. This is one of the really important theorems in number theory, but it's a direct consequence of pigeonhole principle, that you can improve on Kronecker in this precise way, that for any irrational number, you can approximate it by rational numbers very closely, but not too closely. Okay. On the other hand, there are these theorems due to Thue, Ziegel, Roth, for which Roth got the Field Medal, which says that you cannot do much better than Dirichlet. Dirichlet said that it is less than 1 by q square, and the theorem of Thue, Ziegel, Roth says that it is always greater than q to the power 2 plus epsilon. Okay, these are what one may call quantitative theorems. They are rather precise, and this is not what we are talking about. We are talking about just a qualitative result in the style of theorem 1, density. Okay. So in higher variables, there is this famous theorem of Margulis, proving what is called the Oppenheim conjecture, which says that the values of a quadratic form on the integer lattice is dense in R. If some obvious conditions are satisfied, then the values of a quadratic form on the integral lattice is dense. And for a certain region, this theorem is not true for n equals 2. So it's a bit surprising to me that not only there are no theorems, but there are no precise expectations in higher degrees. It's a subject. Irrational means that up to scaling, it is not rational. Like x square plus root 2y square minus root 3 z square. Sorry? Oh, yeah, yes. Very good. Yes, excellent. Yes. So irrational means up to scaling, it is not rational. And indefinite means that its signature is both positive and negative, and the number of variable is greater or equal to 3. So I cannot say it's a virgin territory. I'm sure thousands of mathematicians have worked, but as far as I could find, there are no theorems and there are no expectations. Okay, so I will be working with abelian groups in this lecture. And the first abelian group that one deals with is, of course, z to the power n contained in R to the power n. And okay, so by expectation in the line following Margulis's theorem. No, that is quantitative theorems. Quantitative theorems are, of course, much harder. And there is, no, we are not, that is too much. That is number theory. Too much, too intricate number theory. What I meant was that suppose you, instead of a quadratic form, you give a cubic form. Then you may expect more or less the same theorem as Margulis. Theorems of the type of Margulis work because there is a group which operates, and that is the point of this lecture also, that when there is a group operates transitively or in a nice way, then you have methods from group theory to help you. But if it's a cubic form or quartic form, and you can make the same statement, take an irrational quartic form in 5 variable, which is indefinite. And you can ask whether its values are dense in R. And I am not sure anybody has made that conjecture. Yeah, I'm not sure. All right. So recall that a finitely generated subgroup of Rn is a discrete subgroup if and only if the following equivalent conditions are satisfied. So, discrete subgroups of Rn are also called lattices if maybe it has a full rank, but otherwise in Rn you may look at Z module generated by E1 and E2 in full Rn, and that is a discrete subgroup. And okay, maybe the obvious example to keep in mind, which is prototype of all things which happen for Rn, is that on real line, if you take two numbers which are not rational multiple or integral multiple of each other, then they generate a dense subgroup. Two real numbers generate a discrete subgroup if and only if they are rationally equivalent. And this is these two statements are a souped up version of this statement about real line. Okay. So there is okay. So you see, finitely generated subgroups may be a bit complicated in Rn. They may not be discrete, and then there is some dense part and some discrete part. And what we will eventually do is take closures of these subgroups. So if L is a closed subgroup of Rn, then the connected component of identity L0 of L is a subspace Rm of Rn. So the closure of abelian subgroups in Rn are vector spaces. Connected components are vector spaces. And L upon L0 is a discrete subgroup in Rn upon Rm. Thus, L is uniquely described by giving its connected component of the closure and a discrete subgroup of Rn upon L0. Therefore, for a closed subgroup of Rn, there is a decomposition of Rn as a direct sum with respect to which L is non-canonically of this form, L0 plus M. Okay, good. So if L is a general subgroup, then you can take the closure and come back to statement 1. And it allows you to understand general finitely generated subgroups of Rn by knowing something about the closure and something about the quotient in which it will be a discrete group. So whatever it is, finitely generated free abelian groups are, of course, everybody, students all know very well. But here we are looking at finitely generated abelian groups inside Rn. There are many of them. They are a little different, but not too complicated. All right. So this is the study of subgroups of Rn. Okay, so next, this is the main part of this lecture, commutative algebraic groups. So connected commutative algebraic groups, I am denoting it by A. A is not an abelian variety necessarily, are built from the following three kinds of groups. Finite dimensional vector spaces over Q, tori over Q, and abelian varieties over Q. In a certain sense, maybe they all look the same. I'm not sure, but Okay, and perhaps this notion of a torus, etc., may be not familiar to everyone, but tori are like C star to the power D, but then there are forms of tori. Like for real number, the torus is built from S1, R star, and C star. Every torus over reals is a product of R star, C star, and S1. These three are indecomposable, and the famous Krull-Remark-Schmidt theorem allows one to say that it is uniquely of certain kind. Okay. The case of vector spaces over Q amounts to study of maybe not lattices, but of the finitely generated subgroups in the previous slides. And there is nothing non-obvious to be said. So in the rest of the lecture, we will deal either with a torus or an abelian variety. There are other abelian groups, but I have not thought about them. I guess there are extensions of abelian variety by tori, and they certainly play a role in mathematics, and but I have not thought about them. Okay, so in each case, the question that is being considered is a finitely generated abelian, just to be sure, subgroup of AQ, and consider the topological closure L bar of L, either in AR or in AQP, and the answer that we desire is about L bar naught. L bar naught, for reals, it is the identity component of L bar. It is a locally compact connected group, and it is something quite simple-minded. And it is not the topological structure, but we want to say that somehow it interacts with algebraic geometry. So for reals, the definition of L bar naught is the identity component of L bar. And for periodics, identity components don't have a real meaning, I believe. In that case, I take it to be the maximal compact subgroup of L bar in AQP. For an abelian group, the notion of a maximal compact makes good sense for the cases that we study. Tori, except for vector spaces, they make good sense. In vector spaces, there is nothing called maximal compact subgroup, but in all other cases, there is a maximal compact subgroup. And so this is the question, and we are hoping that this question has a simple and obvious answer. Okay. So the desired answer is that L bar naught is a subgroup of finite index in BR, where B inside A is an algebraic subgroup defined over Q. Nothing could be simpler. And in the case of QP, it is a little more elaborate. So to eliminate some simple considerations, L is a finitely generated subgroup in AQ, hence in AQP, if it is a abelian variety, then AQP is already compact and there is nothing to be done. But otherwise, in any case, we will assume that L is contained in a compact subgroup. Because dealing with non-compactness for tori is a very simple-minded picture, and I don't wish to deal with that. And this L naught, okay. So the desired answer for reals was that it is BR, And the desired answer for QP is that it is GP to the power L. So maybe I should say that the only compact abelian groups over periodic are compact abelian groups over periodic up to commensurability. Up to commensurability is a word which I will keep using, is that you don't care about finite index subgroups. So for me, periodics plus Z mod P is the same as periodics. I ignore this finite ambiguity. And sorry. So this L bar naught is a certain module of a certain rank. And the question is, what is the rank of that module? And the answer is, what is the rank? And the answer is that the rank is the rank of L. So L is a finitely generated free abelian group. It has a certain rank over Z. And I am saying that when you take the topological closure, your rank doesn't drop unless it is forced to drop. And by saying that it is forced to drop, even though L might be a subgroup inside A, it may also be a subgroup inside a much smaller group. L may have rank 50. It may sit inside one-dimensional one, in which when you take the topological closure, it cannot go beyond one. But if there is a space, it will grow as much as the space allows. So this is the main content of this lecture. Unfortunately, this is too simple. So the main content of this lecture, so people, just to give you a few words, people who study number theory, one of the big problems in number theory is called Leopold conjecture. And the Leopold conjecture is about a certain situation of this kind. You have a certain global units and you want to look at global units inside the periodic units, and you want to say that you don't lose. You don't lose the rank. Anything which is integrally independent is periodically independent. But here it is very general, and yeah. So unfortunately, it is not true. And okay, fine. So this is the conjecture, the desired answer for A, if A is the desired answer holds, if A is either simple over Q or if A is RK over Q of GM. So in these two cases, I am suggesting that the conjecture holds good. And in fact, for simple cases, if it is a real topology, then one is saying that L contained inside AQ is a discrete subgroup of AR, or it is dense in AR. Yeah. Extensions. As I said, I have not thought about products. You know, my extensions are products. The category of tori is semi-simple, up to tensored with Q. My questions are invariant under tensoring by Q. Sorry? Yes, 2 would contain Leopold, and in some sense, Leopold has been a model for me. But let's keep going. Everyone okay with this? AR is a certain torus, and AQ, the point might be a point on that torus, and there is what is called the winding line. One is saying that you are always in the situation where a single point may generate everything. All right. So some comments in the Archimedean case. The conjecture above in the case of tori asserts that if a certain tuple of algebraic numbers are multiplicatively independent, then they are independent over R if there is enough room for R independence. Okay, so I should have made some slides on the Chanuel conjecture. Very general conjecture about algebraic independence of logarithm of algebraic numbers. It is like Riemann hypothesis in transcendence. All theorems in number theory follow from Riemann hypothesis, and all theorems in transcendence follow from Chanuel hypothesis. Chanuel hypothesis allows you to prove almost all theorems on transcendence. But this one doesn't seem to follow. I am sure it will follow, but not by me. And the other remark is that in an earlier work, I looked at the question over reals, in which I was looking at finitely generated subgroups which were a bit big, which contained lattices in the tori. And then I did prove the answer desired here. So if the finitely I looked at only those finitely generated subgroups which contain this lattice Tz and proved analogous algebraicity theorems for the topological closure of lambda in Tr, assuming Chanuel's conjecture. And there is also some works of Waldschmidt characterizing those finitely generated subgroups for which this is okay. So typically, as the subgroup you use to take the topological closure becomes bigger, more room for you to play, and they have bigger closure, so their closure looks better. If it is a simple abelian variety or a simple torus, you want to prove that one generated element generates the torus. But maybe you cannot prove it for one. Maybe you need two. Maybe you need three. And there are theorems to this effect that if you have enough points, then they are dense. Okay. All right. So on the other hand, one can also try to construct subgroups which are dense, etc. Perhaps not relevant, but anyway, there are papers which construct rational points which are dense. If I have to do that for abelian variety, that would be a hard exercise. But for tori, looks like it is more by hand. Okay. Yeah. Yeah. No, this doesn't include all tori, and that is, of course, very much unfortunate, and we will come to that. This one is okay. My remark two is a published paper, I hope. Yeah, this is okay. No, but it is based on Chanuel and it is true. So yeah, I mean, for that one is for any tori. Yeah, but No, but you are talking about this remark? No, but here we just want to construct some subgroups which are dense. Not units, S units. I think for units, there is not much of a question because units are a discrete subgroup at K infinity. Dirichlet unit theorem says that units are discrete and for them, there is nothing to be said. The questions are formulated for the connected component of the topological closure. Connected component of the topological closure is algebraic. Okay, so before we come to these questions, I want to review, of course, nothing stands on its own. You base yourself on various things in the subject. And there is this very famous 4 exponential conjecture due to somebody, we will come to that. So observe that there is embedding of Q star in R star, and therefore Q star to the power D in R star to the power D. And therefore, if you take a finitely generated subgroup of Q star square of 2 generators, then they are given by 2 numbers A11, A12, and A21, A22. And then there is this R star is maybe not such a obvious group, but then you take the log and it becomes the Euclidean space. And therefore, the question, yeah, so then observe that the rows of M are Q linearly independent if and only if the group generated by A1, A2 is not generated by one element. The rows are Q independent if and only if the group generated by A1, A2 has rank 2. And the columns are independent if and only if no algebraic character of Q star is trivial on this subgroup. Okay. So these are the conditions which are imposed in the famous 4 exponential conjecture, usually attributed to Carl Ludwig Siegel and T. Schneider. And the conjecture asserts that the rank of this matrix is 2. If the Q rank of a matrix is 2, then the R rank is 2. That's the conjecture. So this is a conjecture almost 100 years old and is still far beyond the reach of mathematics. And this conjecture is exactly what we are proposing. This conjecture is exactly what we are proposing. So in this case, although I don't include GM cross GM, it does include GM cross GM, but there are other products of GMs which are not to be included. Good. Okay, so just to give you a particularly striking particular case, it is not known that the determinant of the following matrix is non-zero. Log 2, log 3, log P, log Q. One doesn't know that this determinant is non-zero. And another form of the same matrix is to say that if 2 to the power t and 3 to the power t both belong to integers, then t is an integer. This is not known. Okay. So this was called 4 exponential conjecture. There is a weaker form of 4 exponential conjecture, which is a theorem proved by somebody at the Tata Institute, one of the very distinguished mathematicians. And this is called the 6 exponential theorem. So a weaker version of the 4 exponential conjecture is a theorem called the 6 exponential theorem due to Serge Lang and Ramchandra, and which asserts something. But the statement is just that the questions are good for 3 generated subgroups if we even if we don't know they are good for 2 generated subgroups. You are looking at Q star cross Q star as the torus, and you are looking at a subgroup generated by 3 elements. And then the 6 exponential theorem in the language of this lecture says that the topological closure connected component is an algebraic subgroup. And therefore, typically it is topological closure is all of it, unless it is forced by some relationship over integers. Okay. So that's the bad news. Conjecture 1 for general tori. So conjecture 1 is made for this torus. This torus is same as what is called K star field, or it is also made for simple tori, but not for a general torus over Q, though it could have been made as the analog of our conjecture is not valid for d greater than or equal to 3. And the particular tori that we have chosen is in the hope that for this class of tori, there are no counterexamples. But of course, you know, in some sense, we need to understand why there is a counterexample. And so anyway, my lecture is just a wishful thinking of many kinds. Okay, so to construct the counterexample, it is all the counterexamples that come up in this subject arise from a very well-known observation to any BSc student that a skew symmetric matrix of odd degree, or d by d skew symmetric matrix for d odd has determinant 0. So this matrix in front of you, it is a skew symmetric matrix, and its determinant is 0. And its determinant is 0 is not something which I can discover. And this needs some algebraic geometry. So my questions go wrong for this particular example. So for this matrix, the rows and columns are Q independent, but the rank of this matrix is 2. You look at the subgroup generated by these points, and they will give rise to that matrix. And so not good, and no clear understanding. I think I have been spending some time, and yeah, I think it's not good to say that it may hold for this case. One must know more better ways. All right. So some comments on the periodic case. So, you know, 6 exponential and 4 exponential are real cases studied by Jigal and Ramchandra. And now we come to the periodic world. This is the Leopold conjecture. So conjecture 1 is the famous Leopold conjecture for L contained in K star, in which case L is not just a finitely generated subgroup, but this particular subgroup. We recall that an equivalent form of the Leopold conjecture asserts the non-vanishing of the periodic regulator and plays an important role in periodic L functions and Iwasawa theory. And indeed, yeah, it would be good to know in what generality one might expect these matters. The Leopold conjecture is known basically only when K over Q is an abelian extension, in which case the periodic regulator is a product of linear forms in periodic logarithm. And there is the periodic analog of Baker theory, which allows you to prove. But in any case, the point of my lecture or my works is not to prove anything, is to find a statement. No, you see, the point is that Q star sits in the R star, and therefore Q star to the power Q sits in R star to the power 3. But R star as a topological space is a bit difficult to know. So you have to use log map. X goes to log mod X to identify R star with R. That is a real vector space. And then 2 in Q star will go to log 2. So I have taken numbers like 2, 3, 1. No, 1, 2, 3. When you do the embedding via the log, it becomes 0, log 2, log 3. And it is this matrix which you want to study over rationals or over reals. The point, of course, is that this matrix is not rational valued. You know, we all know linear algebra that if entries of the matrix are over F, then there is no difference between F and F bar or any algebraic extension, any extension. But here the values of the matrix are very transcendental objects. And therefore, it's rank over Q, meaning rank over Q in this sense, linear independence over Q. All right. Yeah. Yes. Yeah. Right, right, right. Yes, yes. Very good. Excellent. Yes, yes. Okay. All right. So now I have 10 minutes. Yeah. However, even for abelian extensions, I do not know how much the proof of the Leopold conjecture can be pushed in my situation. Need not worry. Okay. So then another motivation for me over the years has been a particular conjecture of Barry Major. And maybe I just want to write that up in some generality for people to think about. So Barry Major wrote a paper or several papers on topology of algebraic varieties. And he was looking at XQ contained inside XR. So take any algebraic variety X, and you look at XQ inside XR. So Barry Major. So his question was that XQ bar, the closure in Euclidean topology is and connected components are connected components of algebraic variety real points defined over Q. So XQ bar, each connected component, so each connected component of XQ bar is a connected component of a variety Y defined over Q and YR. Connected component of YR. So this is again one of those wishful thinkings. you believe there is some simplicity to mathematics. So this conjecture of Barry Major, of course, he must have checked it out with experts in the subject, and this is false. But it is not false for some very simple examples, a bit complicated examples. And so I do not know how to think about if there is a counterexample, what does it mean? But in any case, sorry? Yeah, could be. I mean, for a particular, for someone, it is false. Okay, but then he also suggested that the analog of this conjecture for abelian varieties is true. And that seems to hold water. So even though this conjecture is false in this generality, this seems okay for abelian variety. And for abelian variety, he would say that if you have a simple abelian variety, then as soon as it has a non-trivial rational point, that rational point will be dense in AR. Take a simple abelian variety of dimension 50 and take a point, then that point would be dense. So this holds, and this conjecture was made in the 90s, and now we are 30 years after that. Okay, so for abelian varieties, okay, so we make some comments on the case of abelian varieties over Q, which by model Weyl, AQ is finitely generated. Take a finitely generated subgroup. We consider the topological closure and so on. And I have maybe to fast forward a bit. So here is the conjecture for simple abelian varieties, that if you take a finitely generated subgroup of rank m less than equal to n, then the topological closure of L bar inside AQ is isomorphic to GP to the power m. So no, Barry Major's conjecture is for real topology. This is for periodic topology. And in fact, it is a bit curious that he is a number theorist, and he says that analogous conjecture is not true for periodics, because this notion of a winding line is true only for reals and not for periodics. Meaning a point on AQP can generate only one line, unlike reals where it can generate the whole abelian variety. The obvious thing is that it generates one, meaning it generates as much as it can. So this is totally analogous to the Leopold conjecture. Okay. So yeah, so as I said, Barry Major made that conjecture for reals, and he somehow thought that periodics behave differently because winding lines are not there. But so here is the analog, the precise question for AQ inside AR due to Barry Major, who did not consider periodic case, since jet cannot be dense in ZP to the power D for any D greater than 1, whereas jet can be dense in S1 to the power D. Major only considered the full units in the Leopold conjecture. No, just like the full units, the full model Weyl group. Thus, the following form of the conjecture is stronger than his. A be a simple abelian variety, then one is saying that any non-torsion point is dense. Barry Major's conjecture is that you have to take all of AQ to construct a dense subgroup, whereas most obvious thing to say is that any point is dense. Okay, so once again, that same principle of a skew symmetric matrix allows you to prove that, just hoping non-simple objects, you can create some relations which are not obvious. So, okay, I don't think I can go into that. Okay, so now I come to a question of Madhav Nori. In fact, I did not know about this till this October when I was visiting him, and then I was talking to him, and then he showed me this. So Madhav Nori has rather famous papers on what is called these days super rigidity. Super rigidity, a very brilliant work which has many parts and paper of about 10 pages. Okay, so let pi be a finitely generated subgroup of GL and Q. There is a finite set of primes for which if you look at this ring of fractions, then pi is sitting inside GL and R. So there are two ways to measure how large pi is. One is the Zariski closure and one is the topological closure. And the theorem of Madhav Nori is that they are the same. So the theorems of Nori as well as Matthew, Wasserstein, Weisfeller imply that if G pi is the Zariski closure of pi in GLN, which has finite fundamental group, then the topological closure is open in the Euclidean closure in G pi R hat. On the other hand, if G pi is a torus, then the above assertion is hopelessly false. For example, one may take a simple torus T of dimension Q2 for which a point of QQ cannot generate a subgroup, open subgroup. So for tori, so okay. And however, Nori posed the following question. This is hoping is my wording. He doesn't hope anything. Nori posed the following question, hoping that it has an affirmative answer and reducing it to the case of tori. Is the dimension dp of the periodic Lie group obtained by taking the closure of pi in GL and GP a constant function independent of P, where P is a prime not belonging to S? The lecture here is about taking a finitely generated subgroup of a torus and looking at its topological closure in TQP. And I am trying to formulate something about the topological closure. The question of Nori is that the dimension of what we are trying to do is independent of P. That is, of course, very essential if I want to have a simple answer. And the point of this formulation is that obviously I am going wrong in many cases and I don't understand, but this one seems good in all cases. So this is, of course, very brilliant. Nori noted the relationship of the above conjecture to the Leopold conjecture. It appears to me to be an excellent, weaker version of the Leopold conjecture, valid in much greater generality. Because Leopold is just one case of OK star, etc. And valid also for abelian varieties, though Nori was concerned only with linear algebraic groups. However, Nori did not make precise the number dp, which in certain cases we have, I should have said, we have tried to make precise. There is still the question of making it precise more generally. That number is there. Sorry? No, we need to have a conjectural description of dp. No, it is not. Because of counterexample for GM cube. For GM cube, it goes wrong. Topological closure is two-dimensional, Jersey closure is three-dimensional. But the topological closure is two-dimensional for all P. No, meaning any periodic group is, if it is not finite, then it is positive dimensional. Sorry? Yeah, so no, I mean, yeah, so no, I would not know. Okay, so this is roughly where things are. I should say that there are, this subject is a very, it is not a virgin territory. I think a lot of people have worked on Diophantine approximation on algebraic groups and tori and abelian varieties and so on. There is some notion called structural rank of a matrix. And I am not sure it allows me to understand DP, but yeah, I have been, anyway, this is a question to be understood. Okay, so I guess I don't have much time, but I will quickly say something. Whatever we are doing, that wishful thinking, we can continue to have a wishful thinking. And basically, I think the wishful thinking is that if a group G operates on a variety X, and you look at a finitely generated subgroup inside G consisting of rational points, and look at the orbits and their closure. The question is that in many situations, the closure should be good object. It should be a subvariety. And I just want to end by saying that there is that famous conjecture of Raghunathan, not quite algebraic varieties, but I take algebraic varieties in a loose sense. G mod gamma is also an algebraic variety. And we will look at closure of subgroups in G inside G mod gamma. And Raghunathan's conjecture is about connected subgroups operating on G mod gamma and their closure. Whereas I will be looking at finitely generated subgroups and their orbits and their closure. And I have talked to a few people on the paper in general, but I don't get enough feeling that people have studied these questions, and there is much to be studied. All right, so I think, yeah, so there is Raghunathan's conjecture, but that is about connected groups and their orbits and their closure. Connected groups orbit, whereas I am talking about finitely generated subgroups of GQ, their orbits, their closure in GR mod gamma or in other spaces. Now, but those are details. Yeah, no, but I'm saying that those are matters of detail. But the point I'm making that he is working with connected groups. Connected groups are very easy. Whereas we are looking at finitely generated groups, which are like, who knows? Yeah. Operates on X is defined over Q. G is a variety over Q. X is defined over Q. And the optimal answer is that orbit closure are in the sense of Barry major. Same sense. And just because there are counterexamples there, I'm sure there are counterexamples. So this is too optimistic. But then in the context of some groups, I make it a little more precise and goes on a bit. And okay, so no, that's all. Thank you. No, there is one more slide. Some references. There are some papers of Barry Major and Madhav Nori. It's a paper of 18 pages, and I wrote a paper and um, there are these other papers and thank you and happy birthday, Kapil.
Any questions?
Yeah. Huh? Yeah, so as I said that Damian Ray has done it for number fields and it looks like a worthwhile exercise. I am sure there are many experts here. Uh, okay, so as I said also that there are theorems in transcendence which says that if there are enough points, then things are dense. If there are enough points. And roughly enough points means that if the abelian variety has dimension G, then maybe some something or the other. And but okay, no, this precise question that you are asking whether there is a winding point over a certain finite extension, that looks no, I'm not sure doable, but that looks wonderful. That sorry, decided. No, it looks wonderful. Meaning large enough is not the word, we want to be precise. That bigger than dimension G or something and they reach a point. Yeah, so no, there are things to be done. I think making precise this DP is something which no, no, no. As I said, this is a very well-trodden subject. No, I don't want to give the impression that it's a virgin territory. People like Masser, Ustholz, Waldschmidt, there is a lot of French school, there is a lot of European school. I'm not sure there is enough American school. No, I think no subject in mathematics is virgin territory. I also talked to Jonathan Pilla, and I think these days, I think the Andre Wood conjecture is another conjecture about density of points, and it has been my wishful thinking for last 20 years that somehow it can be also brought in. Sorry, DP is a notation from Madhav Nori's paper, and he is my teacher.
Okay. Any more questions, comments?
I'm sorry, I couldn't make it yesterday. Alone. I am impressed by Professor Kapil. I first met him when I appeared in Professor's interview. He was there. Not before that. Uh, I joined ISER Mohali in that interview was in December itself, first week of December, I suppose. And immediately he didn't ask any question. He was too polite, and of course, he's very, he's one person who's versatile. He knows about all branches of mathematics, and he was head for, I suppose, uh, 6 years. 6 years when I was here, he was head. He always treated me with great humility and grace, and I really appreciate uh, mm, uh, his mathematical abilities as well as very cool nature. I wish him many happy returns of the day. And I'm able to attend another conference on his 70th birthday. Yes, so I wish I can come and attend his birthday also. It's important birthday, 70th birthday, and I'm sure he'll remain active in mathematics and will be a nice and Mohali with us. All the best of it. I will not use the word retirement because I know you are not going to retire.
So, madam,
Okay, so here's a small gift for for the talk. And we begin the next talk soon in 5 minutes.
But I could tell he was already wise beyond his years. So it's not often that I meet somebody as a graduate student when I wasn't a graduate student later, and then still interact a lot mathematically. So it's a great pleasure, and I always like to work with people who think differently. And I think I learned a lot of geometry by working with them. It's really, really great. So anyway, I'm going to talk about higher congruent number. And I could say that I got in practical mathematics already in high school, like probably most or all of you. And the problems that interested me are actually at that time that I didn't know much structure was Diophantine equations. They're just simple polynomial equations with integral coefficients, looking for integral solutions. And then in the past year and certainly, and maybe even before, I've been trying to see all that complicated maths I learned over the years of various types, whether I can put them to use to go back and say something about some Diophantine equation. So this is one of the things. So anyway, I want to talk about higher congruent numbers. Yeah. I hope you can read my handwriting. Words and rational points. And the most important thing I should say here is joint work with Christopher Hines. And symmetric, very much like almost like we had to guess. You would think he's Kapil's student, not mine, because he's more geometric than I am. But it's been a great pleasure to work with him, and I've had some very, very good students. I don't know, just luck, I guess. He's really one of them. Okay, so maybe I should say here, what is the classical problem of congruent numbers? Is you want to look at right triangles and see, and so the problem that people considered long ago, I think it was the Greeks, but maybe other people. So the point is that so you say that number A is a positive integer, is a congruent number. If and only if there is just a rational right triangle with area A. So so what do I mean by rational right triangle? It just means beside the rational. So of course we're going to have it as two equations, a squared plus b squared equals c squared, and then you want the area 1/2 with capital A. Okay, so so if you have such numbers, then you just so I should say that Fermat actually was very interested in this problem already for, we considered the case when A is 1. So we took a congruent number, and maybe I should tell you what he did. So he said that suppose you had a solution. So suppose you had whatever this equation is satisfied, a squared plus b squared equals c squared. 1/2 AB is 1, right? So AB is 2. When he said consider, I think it's a very, very beautiful proof. So he said, so you consider x to be c over 2 and y to be a squared minus b squared over 4. By the way, he always thought of A as being bigger than B. It's not necessary, but we could think that way. Not important. So you take this here, then if you think about it, it's a very good exercise to do. Then take x to the 4th. So if you take y squared, it's really x to the 4th minus 1. So this actually led to him actually studying. So so this is a quartic equation. So actually this led to him studying u to the 4th plus v to the 4th equals w. So in fact, Fermat's equation in some sense came from this attempt to understand this. And he showed that there is no solution. So Fermat proved that there is no solution in integers. So you could, of course, x and y are rational numbers, but you can clear the denominators, and you can get to this way. And then no solution in integers, and then he used by infinite descent. I'm not giving all the details, but you could try to fill the gap. And that's also the first place I've seen him use infinite descent. So if there is a solution, positive solution, UVW, then there is a smaller positive solution. And then go on like that. So eventually it can't be. So it's a very nice result. So 1 is not a congruent number. In fact, Fermat also proved that where 2 is not a congruent number. But then other people studied it for 3 and 4, and it's the first congruent number is 5. Right? And it's not an easy thing. Actually, people knew that it was a congruent number without knowing exactly the size, exactly. And Xavier found an example, and they're really large. I mean, ratios, I mean, very large. Of course, not in size. I mean, it's a ratio of 2 large numbers. And unfortunately, I didn't bring it. So anyway, so there are lots of beautiful results about this congruent numbers. The most, but there's a systematic study of congruent numbers started later. So when you look at things like a squared plus b squared equals c squared, you see that anytime you have such a thing, then you know maybe the first course in number theory that this corresponds to a point in the projecting line. So it's a rational point. And then when you put in the extra condition, half a b equals a, I'm not going to give this because when I will describe better in the higher case. But so what it does is that it gives you a rational point on EA, which is on an elliptic curve. EA, which is like, you can write it in different ways. I write it like this. When this is known to be a CM curve, yeah, it's a CFQ, yeah. Yeah, I was thinking over the algebraic closure. It's, yeah. Yeah, of course, it's conic. And yeah, so when I draw pictures or something, I'm gonna try to draw a real or complex picture. But of course, you have to be, yeah. So, and what is really interesting is that the solution here gives you a rational point, but it's more than that actually. In fact, this rational point must be of infinite order. And you might ask what happens. Well, it turns out that for these curves, so this is actually the curve y squared equals x cubed minus x is a well-known curve. And this is a twist of this curve by A. So actually for each number A, you get a twist of the fixed elliptic curve with complex multiplication. And the point is that the structure of the points of finite order is very simple for these curves. So actually, you can see that you actually get a point of infinite order. And that is really important. And what people realized after a while was that the Birch-Swinnerton-Dyer conjecture says that the rank of the sphere is the order of 0 of some L function. Okay. And in effect, the Birch-Swinnerton-Dyer conjecture tells you whether you can completely solve it. If you knew this, then you would know whether A is a congruent number or not. Yes, maybe I should write PA here. So what I'm saying is A is a congruent number, even only if there is this PA of infinite order. And then this, of course, means that this implies that the rank is greater than or equal to 1. And this means that the L function. And what happens is that you have a fixed elliptic curve and you have all these twists by A. And what happens is that this is a part of a general philosophy. The L function actually has rank 0 or 1 typically, except for some small exception. It's always 0 or 1. Therefore, effectively, that's why I meant effectively, to know that there is an infinite order is the same as knowing that this L function vanishes. So there's been a lot of it. So one could give many lectures just about the congruent numbers. I'm not going to do it, but there's been great recent achievement, whatever, in the thing here. And it's due to, maybe I'll just give the name, the ATM. The two people I would say are very important, like ATM and Ashai Burungali. And of course, they had to use some work of Chris Skinner, and there are more names. I shouldn't say, yeah. So I'm going to let you, there's a very nice exposition by ATM about this whole thing. We'll see him. Yeah, absolutely. Yeah. So I was going to say, in fact, the CM curves are very nice because their L functions are the L functions of the Grossum tab or Hecke-tab. Again, so therefore you know a lot about it. In general, you know very little about it. But the CM ones are very nice. Essentially, okay. So but anyway, the point is that it's not always true that a given number is a congruent number, but maybe I should have said here, there are many numbers are congruent numbers. And I'm always interested in cases where you try to see something is true. And it's interesting when it's not always true. And it's also not never true. So makes it interesting, I think. Okay, so that's all I want to say about that. Okay. So for now, I want to think about the same problem, similar problem in a one dimension higher. So what I want to do is that I want to look at right so I want to look at rational, instead of rational right triangle, I want to look at rational right tetrahedron. So the same thing, I want to, by the way, my picture is going to be bad. So essentially what I want to do is I want to look at three in the one dimension higher. So I take one vertex where I take three edges that are at right angle to each other. So I take the rational right triangle, right tetrahedra, and then I want to, well, I can write A, B, C, A, H. Yeah. So I want to look at the rational. So I want to say a number B is a higher congruent number. I'm going to call it HCM, if and only if it is the volume of a rational tetrahedron. So, okay. You mean like the area? I'm not imposing any condition on the areas. If you impose a condition on volume and the area of one thing, then actually it becomes harder. It's almost, yeah, I can, yeah. Yeah, I don't want to do that. I mean, there are a lot of questions you can ask. Like, given a congruent triangle, can you attach to something, right? And you can solve this. But many questions you can consider, it seemed like either they were easy or they were almost impossible. And this seems to me like it's kind of interesting. I hope you find it interesting. Anyway. Yeah. B is 1,680. You see, and then you have a whole bunch of, okay, all right. Yeah. Yeah, and then of course you have all the Pythagorean for the different triangles, the faces. Yeah, so you have to satisfy all those conditions. Yeah, so yeah, okay, so you have, I won't write down all the things here. You have a squared plus b squared equals c squared, etc. Right, you have h squared, or a squared. And then there are other things, right? A squared plus h squared. The other one, I don't know what I called it, etc. Whole bunch of it. Huh? 1,688. Yeah. Oh, it depends on how I wrote. Yeah, LT88. Yeah, exactly. Thank you. Yeah. No, I do have it. Okay. So I think it's well, it started as kind of a fun project for us. One day we were playing with it, but like Rajan suggested, we tried different things, and it turned out to be either too easy or too hard or impossible. So we wanted to find something that's kind of like the congruent numbers. So sometimes, but not other times. And it involves some, we hope, some interesting geometry. So hopefully it fits with me. Okay. Essentially, another reason I should say why I'm interested, my interest has always been, in some sense, to try to understand rational points for algebraic surfaces. So there is so much known about curves and great things. And I've always wanted to do something but surfaces, and I've tried different sorts of surfaces, Hilbert modular surfaces, Picard modular surfaces, and so on, which are kind of where you can use theory of automorphic forms and think this is different, or abelian surfaces, and this is. But one of my main interests is to study surfaces of general type, which is like curves of genus greater than or equal to 2. And unfortunately, it's not true that for surfaces of general type, the number of rational points should be finite. But there is a very beautiful conjecture of Bombieri and Lang, which tells you that, the rational points must lie outside a finite set of points on rational or elliptic curves. We don't know that. And that's something you can prove in some cases, but not always. And anyway, so I wanted to know if there were some interesting things here. And as in the contour number case, as we see here, you have an elliptic curve. It, in some sense, it's the covering of it over P1, let's say in the. So, we wanted to know what sort of geometric objects replace that. So, okay, so I can tell you, yeah, of course, here there is a, yeah, there is also a relationship A over B times B over H. I know it's a stupid relation, but I like this. Well, and if you, it's a trivial relation, but that's, in some sense, it gives you the right equation. So anyway, so what it turns out is that in our case, in this case, I'm gonna so P1 gets replaced by a K3 by a K3 surface, and then EA gets replaced by a surface XV on general type. And here, of course, the EA is a double cover of P1. I should have done it differently. And here, XV is a triple cover of 1. Okay, so maybe I'll just give you the, if you do the arithmetic, then and you make some change of variables, very soon I hope that we will post this sometime. I mean, very soon, maybe in a few months. You can see the details. And so what happens is that this Y here, so what is Y here? Well, look at this case, the P1, the rational curve came from just looking at right triangles with rational right triangles without any condition on the area, right? When you put the condition on the area, you go to the elliptic curve to the double cover. And the same thing happens here. Here, what can we do? I already erased my picture, sorry. It's so you have this rational tetrahedron. So you could first look at the condition that you have a rational tetrahedron without any volume, right? So that's, so in some sense, Y here, so a point, so giving a point on Y of 2 in some sense, so this is like giving a rational right tetrahedron. But actually, yeah, so if you like, there's an affine, there is a part Y0, which is an affine surface, and giving a rational point is exactly like giving a rational. And you can complete it for various reasons. After fiddling with it quite a bit, you can certainly take a resolution, a nice resolution of this inside T5, but it wasn't very nice. So we found that it's much better to, so the y0, it's much better for us, we found out, to take a closure inside P1 cross P1 cross P1. It's just somehow things are much nice. I mean, what I mean is the singularities are not very different. There. So it's inside. So then, so maybe I should have said here, being in y0, 2, so this corresponds to the equation x squared minus 1 over 2x and y squared. So I have to change variables, but 1 and then y0, and then there's also this x being sub 0, or maybe I should write 0. X means 0, and that has this equation together with another equation, and the other equation looks like this: 6b w cubed. So it's, you've got x, y, and a w. So this is the equation for the x b0. I mean, the equations are not hard. They're just, you have to just change variables and write them this way. I mean, you play with it for a while till you get good equations. But so anyway, first let me say something about y. So what happens is that again, so b is a higher, so the lemma is somehow, I'm not giving all the details, but it's a higher congruent number. So this is an n. A number, if and only if there exists a rational point on x b0. So in the affine part, huh? Yeah, exactly. Yeah. So if you take the compactification, the other ones are going to correspond to degenerate situations. By the way, even in the classical case, it's not true that you get, what happens if you take a point of finite order in the classical case, you get a degenerate triangle. So it happens in two ways, either it can be a line or a point. So here also it's the same thing happens. So if you're outside this, you get something that doesn't work. Okay, so please stop me if you have a question, especially if you're students. So I'm coming to that. Yeah, of course. Yeah. Otherwise, we can do nothing. By the way, I'm going to give you an example of a higher congruent number. I should tell you that one of the things that interests us, but we thought we were close, but we didn't work out, is we think, for example, 1 is not a higher congruent number. We can't prove it yet. I mean, Fermat's theorem should continue here, right? No, it's kind of tricky. So it's an open question so far, but we are hoping to solve that. So because it should be, but you can see from our construction, it's not likely that everything is a congruent number. It's so, but I want to explain that. Okay, so yeah, I'll explain. So this, okay. So actually, so yeah, so if you think of this y0 or if you write it in terms of coordinates, you know, x0, x1. So I'm thinking this is like x and then y0, y1. Z0 is 1. So this is like x, y, and z, right? In the p1 cross p1 cross p1. Then the equation looks like x0 squared minus x1 squared It's very concrete, actually, all this stuff. It may not be immediately obvious that things you have to reshuffle things, but it looks like this. X0, X1, Y0, Y1, Z0, Z1. Yeah, so this is 0. So this is the equation there. That's fine. Equation. There are a lot of nice symmetries here. So there exists, certainly it's clear that you've got action of S3x, and also you have Z mod 2 to the 4 x here. And there, okay, it's kind of fun. It took us a while. There exist 5 involutions. So XYZ, I'm writing sometimes XYZ for this here. So one of them, like minus X minus Y. These are easy, but I'll tell you what took us a long time. What took us a while to figure out. And again, I should say, Chris Lyons was very, very helpful to work with because he really understands some of the geometry involved much better than me. XYZ. So anyway, similar. But there's the first one. I don't think so. Oh yeah, I think it should be minus. Yeah. So there's another involution which really surprised us, which is XYZ goes to 1 minus X over 1 plus Y X, 1 minus Y over 1 plus Y, and then 1 minus 0. Kind of nice. So you have lots of involutions. Whenever you have such involutions, which is really good. And then when you compute the canonical bundle, we did. So maybe I'll just tell you what it is. The canonical bundle turns out to be trivial in this case. So you get rational. So it's trivial, and also you get H1, or if you like, Q is also 0. H1 0 is there. Okay, so therefore you get a K3 surface. So why is K3 surface? So K3 surfaces are just natural generalizations of elliptic curves, surfaces. I somehow think it's more an analog of elliptic curve than abelian surfaces. So I counter. I really think, and in general, they're Calabi-Yau. And I should say that one of my very happy papers with Kapil, we studied Calabi-Yau varieties, conjecturally attached to modular forms. And so, in fact, we wrote both papers that had to do with Calabi-Yau. So anyway, K3 is just a Calabi-Yau surface. Yeah, this Y is smooth. Well, you mean after you resolve the singularities? Yeah. Well, Y is smooth the way I've written it because, oh yeah, if you just take the closure, it's not smooth, but the singularities are just simple singularity, which you can resolve. Yeah. It's a projective variety. Let me check my notes. Hold on. They're just ordinary double points. So yeah. It's very minor. You do have to grow up with some ordinary double point. That's about it. Very simple. But I'll tell you where the double. I mean, if you like, Yes. Right. Yeah. So if you like, okay, so what we did analyze, okay, so yeah, is that, so so anyway, there's more structure to it, so which we want to exploit because, okay, so let me just say, the canonical bundle is trivial, Q is 0, and yeah, yeah. Yeah, this is 0 because if you like, Y is ample in P1. Okay, so Y is K3, but now there's a natural projection. Well, there are really 3 different bonds, but anyway, there exists natural projection from Y to P1, which is just take this X, Y, Z, if you like, the coordinates tend to Z. In fact, you could do it to X or to Y, but I chose Z, but it's not much different. So actually what this does is that this thing here, the general fiber of this projection is an elliptic curve. The elliptic curve. So therefore, it's an elliptic K3 surface, which is very good because we have a lot of structure. So, and then if you like, there is this, I won't go too much into it unless people want details. 8 singular fibers. I mean, it's important to us. There's 8 singular fibers, and they are either at Z is in is 0, plus minus 1, or infinity, or Z is this took us a while to understand. Plus or minus 1 plus minus. Where? Here. And then what happens is this thing here, Kodaira type is I4 and here is I2. Anyway, we can compute the Picard number of the surface. Then it turns out that the rho Y is 20. So it's actually very nice. So it's actually a singular K3 surface. So that means, of course, it's a Kummer associated to a CM elliptic curve. So the upshot is Y is a Kummer. So, and same, sorry, what I mean is, when I say associated CM elliptic curve, I mean it's somewhere associated to E2, where E is the CM elliptic. That's what I mean when I say it's associated. Yeah, right. Yeah. Yeah. So, sorry. Yeah. So I'm going to come to that. So the first thing I computed, first thing we computed was we looked at actually the zeta function. Maybe that'll tell you just a minute. So we identified everything more or less. So so now the H2 of Y, of course, because it's K3, the rank is 22. But if you take the transcendental part, which is the interesting part, that's of course the 2-dimensional representation, because rho is 20. And then we identified it by computing the number of points mod P and using a theorem of current faulting. We actually identified this. This is generated by like mod to the form f of z, which is like zeta 4z, eta 8z to the fifth divided by
Eta of 2
Eta of
16 Z.
So this is the weight 3 modulo.
Plus A3 plus 1, July.
And so this is level 32.
And CM
By
Q squared minus 2.
So this Hecke character is actually the square of the Hecke character. Minus 2. Minus 2. Not minus 2. No, minus 2. Why minus? It's minus 8.
Do you
prefer minus 8? No. Yeah, it is. Yeah. So anyway, so we were interested in this. So H2. So of course it's a Kummer associated to some E, and we are in some sense interested in symmetric square, which splits and gives you this. So the nice thing is we could identify all these things. And so we could actually compute when it has points of infinite order, etc. So anyway, so when did I start? You remember? No, really? No, it wasn't. 12:35. 12:30, there it wasn't ready. Maybe 12, at least 12. Huh? No, maybe minimum. Over complex number. Yeah, that's what I was going to come to tell you. So it's not over Q. It's only over, so it's a Kummer of this over
actually Q? Yeah.
So yeah, over C, but you can make it more precise. Minus,
Yeah, Q squared root minus 2 minus 1.
yeah.
Yeah. Two projections, yeah. First two projections. Yeah. Right. Yeah. Yeah. Yeah.
Okay, so sorry, I may not be able to.
Okay. So maybe now so then remember we have this
Not over Q, but you have to go to a base change. Yeah. I think that's not a. Yeah. Okay, so remember our
XB was over Y.
So XB had two equations. So maybe I'll call it 1. And yeah, I called it 1, and this I didn't call it 2. So the way we try to understand XB is that we try to understand another surface ZB, which is another surface. So this is just defined by, see, Y is independent of V, but ZB, I'm going to take the other surface just defined by the equation number 2. And then our XB is going to be a 2 maps XB to Y. And then here it goes also to V. So we could understand ZV and then know something about XV. So I don't know how much you want to say. We computed all the invariants and everything. It was a bit complicated, but so
So it turns out that this is also an elliptic surface, but not K3.
This is one of those surfaces they strangely call elliptic surface of general type. I mean, I know it's an oxymoron, but they mean, I don't, but people use its terminology in classical language. So it's just a,
And it's Picard maximal. So it means rho of the okay. So anyway, it has a nice structure, but it's not K3. And then XV is a bit more, even more complicated. But what we can prove is that this is of general type. So of course, XV contains XV0 when open. And the points on XV0 are exactly the points we want. Those are the corresponding to the higher congruent numbers.
okay. Any questions so far? No? Video of the map, two, oh, two, this is two, this is three. Please, huh? Eta, oh,
Sorry, eta to the 24 is delta. So it has a modular form of weight S.
so this is weight one, this is weight five, and then here weight two.
2, and you divide it weight 3.
It's very important to us that
You can identify this. That was our main, whenever, I mean, I try to do this, maybe it's because that's the only thing I know. When I take some surface, then I try to see if I can identify H2 transcendent with some model. Yes. Then it gives a lot of structure. Just like in the classical case, why did they make progress on congruent numbers? Because they can tell that elliptic curve with CM. They knew the H1. They could associate it with the modular form of H2. So it's just that things are harder that, okay. I don't know if you want all the numerical invariants, but if you want. So one thing I tried was, okay,
Things of general type, all we have is the Bombary line conjecture that the rational points are contained in some device. We don't know that in general. It's a very big conjecture. But there are special cases where you can try to approach it if it's, for example, if it's hyperbolic. But hyperbolic means that you have C1 squared is 3C2, and it's far from that. It's not hyperbolic. If it were hyperbolic, in fact, Land's conjecture say there should be only finitely many things. So what I believe, maybe with totally no good reason,
but an XV0 of Q, or this, I think should be finite.
but I don't know how to prove that. Of course, what I
I
mean
mean is if you take the Bombary line,
the other curves would contain all the rational points. We don't know that. But anyway, we did calculate for XV all the numbers.
C1 squared turns out to be 48, and C2 is 120.
So it's not hyperbolic. It's not even what they call quasi-hyperbolic, which means that it has only elliptic curves, finite number of elliptic curves and rational curves. We don't know that. So yeah. So yeah.
Sorry?
Yeah. Right now, let's see. We haven't investigated too carefully. The reason is, except that there is some resolution, and the reason is all the points we want won't be lying over the divisor of y, about
you know what I mean? The points we want are outside. And- yeah. Right. Yeah, you're right. Yeah, there's much more to do. It's actually only recently you figured out that it's moving slowly. But we do know quite a bit. But okay. Yeah, and then also I should say PG is greater than or equal to 13. So if you try to look for a modular form, then it's complicated. It's not. So all I'm saying is I'm more saying that as a negative thing. Don't know much about it. However, we can. Yeah. 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 Oh. Yeah, we haven't calculated it. Yeah, yeah. We should. You're right. There's a lot to do. Yeah. But right now we are trying to understand XVD better. And if you want, I mean, we did find something very interesting. Yeah, that's for XV. But first we computed all these things for ZV. And the nice thing that happens to ZV, maybe I should say, is that there is a dominant rational map from two curves. Here, actually. And this curve is y squared equals x to the 6 minus 1. And this curve is y squared equals x to the 6 minus 36d. Yeah, two genus two curves. So you can at least understand quite a bit here. That's the only way we can understand it. Because it's not the K3. Of which one? Both? Oh. This is a rational map. It's not an active. Oh, XB to Y. Yeah, so, well, XB, we really only understand XB0 to Y0. And then XB is built out of some abstract theory of some compactification. We're not as, maybe Chris understands it better, what the compactification is more precisely. I'll have to think about it. Yeah, I don't want to say something wrong. So maybe let me think about it and tell you. But- No. You mean where? On the open? On it? No. Oh, no. No, I mean, no. Not an XV, no. But we're going to use Y. By the way, we have proven what I hope to be interesting theorem. So I'll get to it. I have only 10 minutes. So let me get to it because we proved something, which I hope is interesting. Because that was I'm kind of, our motivation is the higher congruent numbers. I don't know what's. Is it pigeon? I don't know how you do. Okay, so maybe I should say here, there is a theorem. I want to say that there exists the which are HCX. So I want to, this is our only theorem so far. But in fact, we can prove they're infinitely. In fact, we can also prove they're infinitely many cube classes. Remember, we can always modify things, or you can multiply everything by a scale, and then you'll get another example where the volume will be cubed. So without trivial modifications, there are infinitely many. So okay, so then yeah. What do you mean? Non-degenerate meaning they are and I say they're HCMs, they're non-degenerate. Yeah, exactly. Okay, so maybe I should say what the idea is. So it's like, I think of it as collapsing. Yeah, you can collapse a side or a face. Right. Yeah, you can take a bad one and increase the badness. Anyway, we're not looking at that. Okay, all right. So what is the idea? So the point is that, you have this y, to a map to, well, y0, right? P1, and so this is, so inside this you have the open set, which is not, so anyway, which is not, but there are some bad points, 0, plus, minus 1, and infinity. These are the bad points. So this is the bad locus, right? So now we choose, so now pick any z0, which is p1 q minus 0 plus minus 1. Okay. You take in the open, so you take the z0. Now, such that the y z0 has positive model Bay rank. Remember, y z0 is the elliptic curve over z0. And since we know what y is, we know the family of elliptic curves, we can figure out the root number or various things. We can know. So of course, there's a danger that maybe they're all model rank 0. It's not. So it happens, they fluctuate. Sometimes 0, sometimes 1. So you take one where the model rank is 1. So now you choose the point x0, y0. By the way, this 0 is the bad thing because it's not the 0 I use in the coordinates. I don't know. English, somebody told me that when in 20 years or 30 years, when we all use Chinese characters, we'll have many more choices. And we, anyway, choose x0, y0, z0. So this is a point of the y z0, q of infinite order. So we choose something of infinite order. So of course, then of course x0 and y0 can't be 0 plus minus. Okay. Now, essentially, this may be the last thing I say, but anyway. So now consider 6v. I'm going to just look at this equation. So f of x0 over f of y0, where f is the equation, the function we had before, x squared minus 1 over x. That comes in the equation of the congruent numbers. So then when you do this, then you see that now write f of x0. This is kind of what I'm doing is kind of elementary. So everybody should be able to follow. But so you write it as a over b, your rational number. And we can write a and b to be co-prime and b positive. Then okay. Then I should be able to write a as epsilon times m cubed p1 to the p1. P of c, pr to the cr. I know it looks kind of stupid, but epsilon is going to be 0, 1, 2. Actually, I should put cube. because it's coming from cubing something. So this thing here and B can write as some n cubed times q1 to the p1. and q. Yes, so you write everything here like this explicitly. No, just they're distinct. Yeah, that's what I was going to come to. If you just take 0, 1, then I will allow. But yeah, I'm taking them to be all odd. Yeah, I should have because I removed the 2. Exactly. That's why I put this here. Yeah, it's easier. Then once you do that, actually, then you get the W cubed, whatever this thing should be, f of x0 divided by v f of y0 be a over vb. So, and then if you just, so you will get something here. And essentially, of course, we're going to pick b. We can be like v0, be p1 to the c1 up to pr to the cr, times q1 to the 3 minus b1, etc. up to qs to the 3 minus ds. I should have said here something very important that I forgot to mention. I can choose it so that these C's are also between CIs, yeah, and DIs. We can also take into the between. Okay. So therefore, these are all non-negative. So I get something like this here. Now I take this V, and the miracle is that then if you check what happens that then this point x0, y0, z0, which we started with times w, maybe I should have called it w0. This thing here belongs to xv, xv0. So all I'm saying is we fail to really understand it, but sometimes you can't give up. But I felt bad. You need to find if there are congruent, higher congruent numbers. But what happens is that if you look at this map here, so you've got xv0, and then you have y0. So if you take a point here of infinite order in some, so inside it you have y z0. And then if you take a point here of infinite order, somehow I can find some v. Not, doesn't work for all v. It's some v for which I can choose, and then I can solve this problem. So that's what we were initially trying to see. Given a v, we try to really understand this, etc. We couldn't. Maybe you can, but so far, but we could still solve this thing. Maybe I'll give you a numerical example and I'll stop. It's a bit tricky to say that there are infinitely many, but so maybe I should give a concrete example. As I was saying, this is the kind of stuff I would have been interested in high school. When I was finishing high school to know about higher congruent number. I mean, I wasn't, but would have easily been something I would have liked, and I didn't know much math, so, but you could ask. So therefore here, so the example is you take Z to be 3/4, and then it turns out explicitly the rank of Y 3/4 is 1. It's just because we know. This is because we know Y. Really important. So once you have this, then it turns out that x0, y0, z0, this point on y0 or yz0, maybe I should say z0. So this thing here, we choose this following point, which is 11 over 21 minus 1 over 10 and 3/4. So this is a non-trivial point of infinite order. You could just check it by computer or whatever. So maybe I couldn't have done Anyway, so it's the kind of thing, so you can actually do it, and then if you go through our process, our procedure works with V0 is 5 squared, 3 squared, 7 squared times 11. Which is, if you like, 121, 275. It's far from 1, right? And it's not small. So each time we take a rational point and compute a point of V, it's pretty big, relatively. So my belief is it's not going to be possible. So, oh, by the way, you can actually prove that if you had a non-trivial point on xv0, it must give rise, it will definitely give rise to a point on one of the elliptic curves, but it has to be of infinite order. So, so anyway, this is kind of nice. Maybe I should stop here. But it's kind of nice. So, but you wouldn't have been able to guess this. Whereas in the original congruent number problem, the first case where we found was 5. Is not, so it's actually, in my opinion, it's a bit more sparse than congruent numbers. However, I can't prove yet that the number 1 is not a higher congruent number. So either we'll prove it in the next few months before we post the paper, or we'll leave it as a problem. Yeah, that it's not. In fact, we don't know a single number which is not. Yeah. Okay. Now, all I'm saying, we hope to solve it. We are working on it. And the thing is, my original hope was you have the ZV, and maybe it's already hard to find points there because it's just a map from a product of two genus 2 curves mapping, but there are points. So that means that you can't do it in a trivial way. Y has lots of points and Z doesn't, only a few points, but they have points. So we can't tell there are no points on X. So anyway, I hope it's of interest because I think of it as some kind of a small bit of trying to understand some surface of general type. To me, that's actually the main problem. Yeah, but it's not. Yeah, but it's not though. XV's motive is not. Y's motive is. So it's kind of intermediate. I mean, it should look at, look, if you believe Langland's maybe everything should be automotive, but we don't know. Yeah, right. You have some model looking on Y. That's why we work hard. Because first we thought it should be K3 and okay, but even if it's a K3, we don't know much about it. If it's elliptic K3, then so that came naturally, but then luckily rho was 20. Once we realized that, then we thought we had a chance. Then the Falking Stair method tells you if you compute for enough mod p, that the number of points corresponds to that's given by another form. Should be. Exactly that. So, and then we tested it also. Right. Correct. So it's very nice. Anyway, it's very enjoyable to me that we could at least partly solve this problem. Okay, thank you.
Any more questions?
Thing about the point being of infinite order.
Right.
Should lead you to a descent method.
Yeah. Right. Right. That's I believe it. Yeah. 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 You're right. You have to use the same somehow. Yeah. I agree. Yeah. Exactly. Yeah. Yeah. Surface of general type. Surface of general type, which is a cubic cover of of the office of an elliptic K3. And it's not K3, it's PGs too. For that. Yeah. PGs too. Yeah. So, right. And we have a procedure to start with the rational point of infinite order on one of the fibers of the elliptic curve. And then we can produce something for some V, not for any given V you start with. So therefore, we start with Y. So if you like, and maybe find a rational point in infinite order, and then there is some V where we can find a point for XV. But that V turns out in all our examples, the of infinite element seems to grow. So like if the point is at certain level, it gets bigger. Right? Yeah, yeah, okay. Yeah, maybe we should start.
Any more questions, comments? Okay, let's thank the speaker once again.
So welcome back, everyone. So our first speaker for this session is Professor Nitin Netsure from Bhaskaracharya Gujarat. He will be speaking. The title of his talk is Ital and Food Morphisms.
Thank you very much. It's a great pleasure to come here for this variety entertainment program. And Kapil has been a great influence on me. I have talked about it yesterday. You will see some of his influence today also. But it's also very nice to meet various people in the audience, from Ramanan to the youngest of you. Mic is on. Yeah. Can you hear me? Oh, okay, all right. So I won't make the preliminary remarks again. If you have content, you have content. Okay, all right, let's start. So when I thought of the talk here, I had a terrible option, which was half an hour of definitions, because I work in something which is the finer structure of the modularized stack of principal bundles with predictive structure groups in characteristic P on predictive varieties in higher dimensions. And so for that, I have to do a lot of setting up notation and whatnot, at the end of which the experts will understand it who wouldn't have needed all that notation also. So I remembered myself as a young mathematician, and actually things have not changed much in that respect. Going to conferences where almost anything goes boom, so beyond the first few things. So I thought I should use the opportunity to talk to the young. There can be one talk which is mainly addressed to the young, and I request the indulgence of the experts. In fact, they can point out improvements. Correction. Okay, so let's start. So this is the abstract which you already read, which is part of the brochure. And as you see, I have 30 slides, and I note I'm starting at 37. So roughly 2 minutes per slide is the speed at which I should go. All right, so a bit of overview. When I started typing these slides, I was going to type overview 1 and after some time overview 2, but now only overview 1 remains. So the overview 1 tells you why we should be doing this. So historically, Riemann introduced moduli, and for Riemann, it was not moduli space as far as I know, but he only introduced parameters via the Riemann matrix perhaps. And he found there are certain number of parameters required. Then it is really Teichmuller who introduced the notion of families and their pullbacks. And that is what moduli are really about. Families are the main thing. Families of the kind of objects that you want to parameterize. Can you hear me in the back? Yeah. And then Grothendieck studied Teichmuller's stuff in detail. The reason I say this is Grothendieck gave 6 talks on FGA, and he gave 10 talks on Teichmuller. Teichmuller 1 to 10. And these 10 talks are, of course, part of one of those Paris seminars. And in those days, they wrote detailed notes of everything. So Grothendieck completely reformulated Teichmuller in terms of categories and functors, which was his big thing. And also he had scheme theory at his disposal. One of the handicaps of the earlier moduli theory was there was no way of doing deformation theory infinitesimally. There were no Artin local rings and so on. So Grothendieck with his schemes could also do infinitesimal deformation theories and try to take limits, try to algebraize it. All these things came there once he began with Teichmuller's work. And then others, Grothendieck himself suggested the functor of points. Mumford with Deligne and Artin took it much further. They reformulated the spaces on which you do algebraic geometry in terms of functors. So I was introduced to this point of view by Kapil when we shared an office. Kapil used to read an article of Mumford called The Moduli Problem for Elliptic Curves, in which the main result was the homology of the moduli problem of the elliptic curve of the Picard group. Picard group of the moduli problem of the elliptic curves is Z mod 12. That was the main result, which Kapil used to like. He used to enthusiastically describe it to me. There is that black book. Some such. Anyway, in those days, even stacks were not defined when Mumford was writing. And so Mumford and with Deligne and Artin made precise definitions. They reformulated spaces themselves as functors. Those were algebraic spaces, Deligne Mumford stacks, Artin stacks. And in that, étale and smooth morphisms play a central role. There's a certain reason why étale morphisms are needed. That's because the implicit function theorem does not hold in algebraic geometry or Raisky topology. We will come to that. So that's how étale and smooth morphism, which is my topic. I have not introduced it here. Now let's see that schemes and morphisms can be understood in equational terms. You actually write some equations. Like today we have seen very concrete equations, nice equations. So you can begin with equations. Or you can begin in algebraic terms, somewhat more as abstract. Or you can do it in functorial terms. Abdenker used to call it high school, college, and university algebra. But what you, and commutative algebra is closer to the equational terms than the functorial terms, but actually can go back and forth. And you need to go back and forth all the time. Translation back and forth is an important non-trivial problem. The moduli point of view requires the functorial point of view, as Grothendieck reformulated Teichmuller. On the other hand, to really do anything to calculate, you need to do algebra, solve equations finally. So back and forth is very important. So we'll begin with seeing étale and smooth morphism in these complementary ways. Now you know translation is a very difficult problem. Translating between two things, very difficult problem. Historically, the archaeologists dug and dug and dug, and it was hard. And they found a stone, and that stone is called Rosetta stone. So, what's the Rosetta stone for going back and forth between equational, abstract algebraic, and functorial point of view about étale? And then that is applied to smooth. But the digging is very difficult. Digging takes all the might of Grothendieck's, Zariski's main theorem. Grothendieck's, Zariski. All right, so let's look at the Rosetta stone. It goes like this. This should remind you of something. Of course, all the experienced mathematicians know what this is, but the younger people should be immediately reminded of something. I'll say what it is in a moment. So now let's take a ring. Let's take a monic polynomial. Let's take another polynomial such that the derivative gets inverted once you invert this and go modulo f. So in equational terms, that means there should exist some other polynomials h and k and some integer n greater equal to 0, so that some such equation holds. Kapil may not agree to calling this an equational criterion because here it says there exists. There exists shouldn't be part of equations, not Kapil, in some point of view. Anyway, it's kind of logical equational point of view. Yeah. So an algebra of this kind, AX with G inverted modulo F, is called a standard étale A algebra. This is the Rosetta stone. Now, by now, many of you have figured out, this is the primitive element theorem for finite separable field extensions. A finite separable field extension is obtained by A is a field. You take an irreducible polynomial f, which is a separable polynomial, and then go modulo f, that is adjoining one root, and there f prime is non-zero is part of the separability of the polynomial. Non-zero is invertibility because that thing is a field. So the ring theoretic analog would be this. And since if you have something étal and you invert one polynomial, go to an affine open, that should still be étal. So one might as well right from the beginning allow inverting something so that the derivative gets inverted. That is this condition. Okay, so definition clear. So this takes the conclusion of the primitive element theorem and makes it into a definition, generalizing it to rings, and that's a standard étal algebra. This is really one of the cornerstones of the case. You see, for me, this whole journey started when I was lecturing to you guys. Dipendra is there from that audience on algebraic stacks. And then I saw that the students, and there were many young students in the audience, they needed to understand étal and smooth morphisms, and what the best of them knew then, of course, they are very young and they are doing algebraic geometry only for a year or two. They knew what's there in Hartshorne. And the Hartshorne smooth morphism definition is, let's not say. So I needed to set up the theory of étal and smooth morphisms in a convincing, quick way. And I could not find any convincing, quick way. Then I'm running ahead of the story a bit. I did a lot of Google search. Those were COVID days. And I found an article by Jesus himself. You will see Jesus's article and its proof. Rosetta Stone, Jesus, what is this? Now, but Jesus was assuming Noetherianness. And then again, I did a lot of Google search, nothing. Jesus's article also doesn't say anything about non-Noetherian. Jesus's article is forwarded by Kleiman. So obviously he knows what's happening. So then I thought a simple argument will give reduction to Noetherian. I did that. You will see all that. Then I put it on archive. It's a completely simple argument, but then I can say in the class, I told my class that I'm not going to waste time explaining this. I just put it on archive. Archive took 2 months to put it out. By then that course was over. So anyway, then now again I do Google search and I find the argument in Stacks project, but I'm not saying they took it from me. It's a very simple argument. Probably many other people knew it or discovered it, or maybe it was folklore and I couldn't find that. Anyway, we'll come to that. So but still standard étal algebras I cannot fully avoid. The Esqui's main theorem I cannot fully avoid. You will see that. Let's come to that. So now this kind of localization, I can also, okay, let's go back there. This is finitely presented because I can rewrite this localization by adding one more variable and one more equation, which tells you that G is invertible. Okay. And this remark will apply all the time in my lecture, that I will invert something, but then think of it as adjoining one more variable, one more equation. Rank of the system of equations will be appropriately adjusted. Now, this standard étal algebra has some wonderful properties. First of all, because f is monic, this is finite and free actually. Why is locally free? This is a finite free A module, and so it is flat, and so its localization is flat. And since df is going to be f prime times dx, and df is going to be 0 once I go modulo f, and f prime is going to be invertible because I inverted g. That means that dx itself is 0. You see, dx is 1 upon f prime times df. That is 0 in the relative Kähler differentials. And that generates the relative Kähler differentials because x generates b over a. So all different Kähler differentials are killed. So this is what is called unramified. It is flat, it's unramified. And that was the traditional definition of étal. That's the definition you find in many places. It's a finitely presented morphism. It is flat and for which the scalar differentials are 0. I call it étal, and note the pronunciation, étal FU. Okay. Not étal FU. Okay. So I'll call such morphisms étal FU if it is Zariski locally finitely presented, flat and relative differentials are 0. So standard étal is étal FU. Now the second definition of étal. This is the functorial point of view, thinking of spaces as functors. These are algebra. Algebra consists of solving equations. So, but you're going to solve equations. Those same equations you are going to solve in integers and say there are no solutions, but then you will solve them in maybe some extension and then they will have solutions and so on. So you solve the same equations, but you solve them in various rings in which the coefficients make sense. So all of it has to be thought of as a functor from rings into sets. What you're solving your equations in is the ring, and set is the set of solutions in that ring. So generalizing this, all of scheme theory, all of schemes can be embedded by a faithful functor from the set of all functors, the category of all functors from rings into sets with natural transformations of functors as the morphisms there. And so schemes are a full subcategory of the category of functors from rings to sets. So now what is really difficult is to say what is the image of this fully faithful functor. So considering it is fully faithful, you can do a lot of awkward and ugly work and translate having a Zariski open cover into these terms. Never checkable, very, very bad. So there is no really good functorial characterization of schemes via their functor of points. Any good characterization expands the category of schemes. And that shows that you should expand the category of schemes if you want those functorial properties to be true. Okay, so, but there are various properties of schemes which can be captured in terms of their functor of points. The reason this is called Yoneda is for any general category, if you can embed the category itself into the set of the category of contravariant functors from that category into itself. So, but here I am restricting the functor to affine schemes. And that is enough because of Zariski gluing. Zariski descent shows that that's all that matters. Okay, but there are certain properties which can be captured in terms of functor of points. This is a very important property. You know that if I have ring A to B, you say B is finite type over A. If B is generated as a ring, anything can be written as a polynomial in some finitely many elements of B with coefficients in A. So it's a quotient of a polynomial ring in finitely many variables over A. Then you say B is of finite type over A. So you're going model and ideal. If that ideal also you can choose to be finitely generated, then you say it's finitely presented. So finitely many variables and finitely many relations. That is finite presentation. It's like finitely presented group. So, so being finitely presented, this is now what you can demand of a morphism of schemes locally, because given any y to x, you can cover x by affine opens, and each inverse image of the affine you can cover by smaller affine opens. And look at this affine open to affine open, meaning a ring homomorphism. And if you can choose such a thing where these are finitely presented, then you say the morphism is locally finitely presented. That thing can be tested purely functorially in terms of its functor points. And the answer is this. So I gave these lemmas names so that I remember that I have written this, not written this. So this is local presentation. So this is the reference. A map of schemes morphism. The word morphism kept on occupying enormous space on my slides. So I shortened it to map. Ring homomorphism again takes a lot of space. So that's also map. So a map of schemes is of local finite presentation if and only for any filtered direct system Ri of rings over X, which means spec Ri to X are given terms. The natural map of these co-limits is a, from this co-limit to here is a bijection. So you can make out from just purely functorial properties whether something is locally finitely presented or not. The idea is here you will have this increasing union of increasing union, doesn't even have to be inclusion. And you are trying to solve your equations in that. If those are only finitely many equations, finitely many variables, the solution will come from some level. And that's why this will work. Okay? But on the other hand, one of the most important properties that we need, and we saw that standard et al. Was flat simply because it was finitely generated free module, localization of that. So flatness does not seem to have a useful characterization just in terms of this functor of form. A very ugly thing can be rigged up, of course, because everything can be translated. You can set up some category of modules, get into coherent shields, some pullback functor, exactness, some lots of other things will have to be included, which is extra structure than just this functor or this morphism functor. So flatness doesn't seem to have good characterization. Yeah, I mean, I was sitting at home and not having anybody to talk with, not a place, and not like TIFR where you can walk into the canteen at tea time and there will be somebody and you ask, hey, do you think there's a flatness criterion functorial? And you'll quickly know the answer, or you just go down the corridor, not somewhere. So anyway, all right. So let's go on. So there's another very important criterion which is purely functorial, and I'm formulating this. I would have liked to draw a picture and I didn't want to draw it and take too much space on my slides. So let me draw that picture here. So there's y to x homomorphism schemes, and here is spec C prime, and here is spec C, and C is equal to C prime mod I square equal to 0. And there's this morphism. And the question that this is asking is, can I lift it? Are there lifts? This is a set of lifts or this. So one of the things you know, okay, so this is a square zero extension. The square zero extension will lead to spec C sitting inside spec C prime as a closed subscheme, which is topologically the same. I square is 0. So topologically no difference. So topologically this lifting is there, but you want it as a morphism. So if there's a map of scheme for every square zero extension, we have this map. That's just restriction. And then we say this map is formally unramified if given this commutative square from outside. There's at most one lift, making both those triangles commute. Exactly one lift, at least one lift, whatever I have written there. Formally unramified means injective, this means surjective, this means bijective. So at most one lift, exactly one lift. Sorry, at least one lift, exactly. So this is a purely functorial definition. And in moduli terms, this makes sense. You have a family of whatever kind of things whose moduli you want to study, and you have been given a family parameterized by spec C. Can I enlarge it, spread it around to a family parameterized by spec C prime? At most one way, at least one way, exactly one way, etc., etc. Then that gives you information about the moduli space. So this criterion really comes from our understanding of the implicit function theorem kind of situation, because there you say that as a round space, some upspace space implicitly defined, there is this morphism, and I choose a point above which satisfies the equation. Now can I spread it around a bit? And in how many ways? So this converts that into a definition, and these are called formally unramified, formally et al., formally smooth. Okay. So is this definition clear? This is really the cornerstone of what goes on? No, that was Rosetta Stone. This is Cornwall Stone. Okay, so let's go on. So such lifts are related to Kähler differential. You can read so much notation or just look at what I'm saying here. Let me look at it algebraically. So I have C and I have C prime and this is C mod I, and we are talking locally, so this is B, C prime. Thank you. I have A and I have this diagram, and the question is, are there some, what are they, etc. So take the set of all these. This is the set of all possible lifts. And what happens is, once you have this situation of this diagram and I square is 0, that upstairs map was called G. I first of all becomes a module over C because I square is 0. So I becomes a module over C. And I can push it forward and get a module on Y, that is that G low star I. And what you can do a simple calculation and see is that the set of all these lifts is really a torsor under this group, home of omega B over A into G low star I, or better way of saying is derivations, A linear derivations of B into G low star A, which is the same as these homomorphisms. If I take any such derivation and add it to a lift, I get a new lift. Conversely, given any two lifts, their difference will be exactly one such derivation. So it's a torsor under those. As you know, it's being a torsor under some group doesn't mean that thing is non-empty. It may still be empty, but it will be a torsor under this one. Okay. So this is a little calculation you can do. And in case this is a projective B module of finite rank, by finite rank, I only mean locally finite rank, but anywhere finite. Then this home I can write by taking the dual of it. This won't work if the rank is infinite. And then this becomes H0 of spec C with I tensored this by the projection formula. This 0s are on this side. Projection formula of that. That's what it's called. Goes to the other side. All right. So now, because we understand what are the possible lifts locally, those three definitions, formally étale, formally unramified, formally smooth, can be connected to the global behavior to a kind of local global argument. Let me make that argument here. So if I have a map of schemes, then formally unramified or formally étale, if I only, and these three conditions are equivalent. If that's locally so, then it is. And locally so can be said in many ways. There's a point upstairs, I have a neighborhood there, which goes into a neighborhood here, where it is like this, or there is a covering. Uniqueness makes existence always possible, because if you have local existence and uniqueness, then the local lifts are going to glue and give you a global lift. And unramified means uniqueness. So which also works for étale, which is also unramified. So I wrote this lemma very easily for formally unramified and formally étale. For formally smooth, the question arises, I'll have many local lifts, but they'll differ by what we just now worked out. Can I glue them? And that is also possible, and that's the next. Because that then becomes a cohomological question. I have these local lifts. In the special case where the Kähler differentials are locally free of finite rank, it goes to the other side. Otherwise, the local X don't immediately give you global X. Then there will be a speculation. But here, so I can write this lifting lemma. I have these local lifts. Topologically, they are the same, so they land into the same affine open cover. So the problem reduces to algebra, because otherwise the problem will be there is one local lift, another local lift. Why can I choose a common affine open covering in which to study them? But that's because topologically they are the same lift. So I can study them over a common Zaleski open cover. So I have named this lifting lemma for my memory. These are not any standard literature terms. And then in the overlaps, they differ by elements here, giving you a check, one cocycle. And this is an affine scheme after all, and its first cohomology with coefficients in anything partially coherent is 0. And so it will glue and give you a global lift. As I started writing these arguments, see, even when I was a graduate student, my exposure to étale and smooth and whatever was very perfunctory. And to rapidly get into, then the interest was to understand well conjectures and such things. So to quickly understand étale cohomology, little bit of étale morphisms, and quickly étale sheaves, étale cohomology, and then the various results, duality, this, that, or étale fundamental group, whatever your interest was. And then that early exposure won't do arguments at this level, where these are not difficult arguments, but to suddenly bring in cohomology and say this, while étale, smooth, etc. are introduced in an earlier chapter of the book, and the cohomology only comes later. It's like the problem in homological algebra books, where the spectral sequences are often the last chapter. And then so many arguments that we would now do using spectral sequences right from the beginning or derived categories are not done that way. So revisit helps in that sense. Okay. So here's a lemma, and it's only an exercise that formally unramified if and only if omega y over x vanishes. That you saw because it's a torsor over home omega into I. So if omega is 0, obviously it is 0. Conversely, converse also easy to prove, so I am not spending time over this. This is how the converse will work. For the converse, you have to convert an extension, a square zero extension, using the Kähler differentials themselves. And so now if you write your extension using Kähler differentials, which is what happened? Yeah. This is the square zero extension created using Kähler differentials. And then you will get the universal derivation to be 0 and hence this to be 0. So unramified has a very rapid translation. So now at last I'll define a unramified étale and smooth morphisms. Earlier, remember, I had defined étale FU morphisms, flat unramified, étale flat unramified I had defined. Now I'm going to define a new kind of étale morphism whose definition is completely functorial, and that I'm going to indicate by putting a star. All this is temporary notation because I'm going to prove they are all the same, and then the stars and the FU and whatnot will all go away. So a map will be called unramified star. This is the EGS sense if it is formally unramified and locally finitely presented. Grothendieck put in this locally finitely presented. I suppose that's because he had proved that earlier lemma where local finite presentation is completely functorial preserves those limits. Okay. But it became too much and people quickly became unhappy with Grothendieck's definition because you might have scheme and a closed subscheme. And don't you want the closed subscheme to be unramified? Whole world had been calling such things as unramified, and it fits one's intuition of unramified. But the ideal might not be finitely generated, so not finitely presented. So Reynaud suggested a change in definition. So the currently popular definition where you go read unramified is not assumed to be finitely presented. Of course, if you are in the Noetherian case, there is no reason. Okay. So that's the definition of unramified star. Étale star is formally étale and locally finitely presented. And smooth star is formally smooth and locally finitely presented. These definitions are not there in the popular textbooks. Now there's this great source, the Stacks project. And to me, I mean, it's very useful. I try to dip into it here and there and try to understand something. But it's a bit like you're thirsty and you take a glass and you try to stand under the Niagara Falls to get a drink of water, and not just the glass, you also go away. And then it sends you on a wild goose chase, but with very precise numbers. Luckily, because it's modern, it's HTML, so you can click and. So yeah, one has to look at stacks. Earlier, like one used to look at EGA, and there the problem was much worse. French, no hypertext. But then, yeah, again, precise 4-digit numbering. All right. Great, and that was great for your education, no doubt. We became lazy, I think, and after Hartshorne, we jumped into research without spending time on EGA. And you are busy at that age. The problem is waiting. So, all right. So let me prove this little lemma. It's like an exercise that standard étal maps are étal star. This is the prototype of the kind of arguments proof of inverse function theorem. So what you do is you consider a small extension and you want to lift something. So begin with a random lift and you want to repair that random lift by adding a little constant to it from I so that it actually becomes a lift. Because X you can lift anyway somewhere, but to be really a lift this way, to go here, you have chosen something wrong, add the right thing will come by correcting by adding something in I. And now you have to solve for what to add. That becomes just this equation, which you can solve because f prime at that what your C prime is invertible. It is invertible because under a square zero extension, the inverse image of the units there is going to be units. That's the only remark we have to make. And then you can solve and get a unique answer. And this argument essentially was done by, what's the name, man? Huh? You know the guy whose lemma we say, na, and a complete local theme? Huh? Hensel, exactly. Oh, Newton has done this. Newton didn't have infinitesimals. Anyway, Newton had power. Okay, in some sense, Newton did this argument. I agree. But yes, Hensel is what I had in mind. And I got a really bad case of name amnesty. I cannot remember the name stuff. Okay. So this is Hensel's argument. Hensel's lemma kind of it. And while we are at it, I can even state a more general one. If I have a number of variables and a number of equations such that the Jacobian matrix, same number of equations, Jacobian matrix is invertible, then again it is formally étal. Because it will involve solving the same kind of equation. Doing linear algebra is possible there because the Jacobian is invertible. Okay. Okay, now reality check. I have finished half an hour. 30 more minutes, great. 20 more minutes and okay, I should speed up. Okay, so now this is what I discovered and which now I can also find in Stacks project, that smooth star ring maps admit smooth star Noetherian reductions. And here the idea is very basic and very simple. There's a kind of map which is obviously smooth, namely a polynomial map. If I have a polynomial ring over A, then obviously it is, because I can do anything with my variables. I can send them anywhere. So I can always create whatever I want, no problem. Now suppose something sits inside the polynomial, sits inside that affine space, and I want to do the lifting there. Okay. It's enough to do that lifting within an infinitesimal neighborhood. Anyway, it will land in the infinitesimal neighborhood because this spec C sits in spec C prime is a square zero extension. So if spec C has been given a morphism into Y is an affine space over X, and spec C prime, anyway, I know topologically where to send it. So it does go into the first order infinitesimal neighborhood. So it's only a matter of whether the first order infinitesimal neighborhood, it's like a tubular neighborhood retracting to this. So if you have this kind of first order tubular neighborhood retract, inside an ambient smooth star space, then your closed subscheme is smooth star. Get the idea? Now, and if and only. Okay. So this is the lemma. For me, smooth if and only if the question admits to section only. Now, what would a section entail? Such a section would have only finite amount of data because I am assuming these are locally finitely presented. So to define the section, I only need some finitely many coefficients, etc. And I need to say it's a section, to say that to go there and come back, it is equal to these modulo something. Again, some finitely many polynomials will be involved and their products and sums. So by adjoining finitely many elements to Z, meaning creating a finitely generated subring of A, I can reproduce this in equational terms. And in equational terms, it is a first order neighborhood retract, therefore it is smooth. So I have reduced everything to the the finite type over Z situation, which is nothing. This is my archive reference, but I explained it. Now, now comes the big theorem. But you will see it's now an easy theorem. Now, but big theorem in EGA terms. It is that all smooth star maps of schemes are flat. And the proof goes like this. I am going to give a new proof. New meaning it's not mine. One component which was mine is already over. But now comes the component of Jesus. So this was a non-trivial theorem earlier. I'll also give you another Noetherian proof later. In a Noetherian case, it was given a surprisingly simple proof in 2017. This is by somebody called Jesus Conde Lago. He said that any formally smooth morphism of finite type between Noetherian rings, you don't have to say finite presentation, so because they are Noetherian, is flat. And so once you know this theorem has the following proof. You locally make a Noetherian reduction, which is still formally smooth. There it is flat. Flatness is anyway a local property. So flatness is true. So all that now I have to show you is a proof of this theorem J, Kondo-Lagos proof. All that it uses is the relevant chapter in Atiyah MacDonald, some very simple statements about completions of Noetherian rings, and it's true. Totally amazing. So the proof goes like this. So suppose I have A is Noetherian, A to B is finite type and formally smooth. Now put it in an ambient affine space, write it as a quotient of this finitely generated polynomial ring for this ideal, and go to the completion by this ideal I. The important point about being Noetherian is that this is going to be flat. The completion is going to be flat over here. And the ideals completion is going to be the extension of the ideal. All these things are proved in the relevant chapter of Atiyah MacDonald. So now you go on lifting step by step because each of these quotients is a square zero. And B by is formally smooth. So step by step, you can go on lifting the identity to a section, to a section, to a section, all the way to the completion. And therefore, your original B has now become a direct summand of the completion because you have produced a section. And the completion is flat, and so B is A flat. So QED, just this short of proof. Now, here's what I call old proof. I cannot give you a reference, but I thought I should be able to prove it. At our age, it becomes rather difficult to go and read textbooks. So, because one thinks one knows so much, you should just sit down and try to give a proof. So, the next 1 or 2 slides is a proof without it. But then the kind of things I have to use are the local criterion for flatness equation and fiber-wise criterion for flatness and whatnot. Local criterion of flatness again has a very long proof. So I won't show you the details, only to say that otherwise I can do it in the Noetherian case, assuming too many things. But now here's how the Rosetta Stone gets used. Okay. So here's the theorem. Again, this is not easy. The theorem says that if I have finitely presented an unramified morphism, Then I can look, and I have some point upstairs. It's unramified there if and only if I can invert something, localize around it, so that it becomes a quotient of a standard étal algebra. So standard étal algebras are of course unramified. Anything unramified locally looks like a closed subscheme of the standard étal. This proof is surprisingly difficult, very, very difficult, because it has to use Zariski's main theorem. Proving Zariski's main theorem without assuming Noetherian is a big thing. Hudson's book has a Noetherian proof based on homology. But without Noetherian, it was proved simply straightforward in an algebraic manner by Peskin in 1967. I suppose many of you might have seen the proof of Peskin. I gave a series of 3 talks in IIT in January this year. And I see 1 or 2 of you were in the audience. So there I explained the proof. It takes a lot of work. And then Hochster in his notes says that the proof of this involves Zariski's main theorem, the theorem on primitive element for septuple field extensions, which you should expect, because after all, standard étal morphisms are a generalization of primitive element theorem. So that is also the starting point of the proof. Our understanding of unramified homomorphisms in the base ring is a field. Nakayama's lemma, additional trickery, and the trickery is really clever. There's a lot of trickery. It's worth reading this proof in the original, and takes a long time to explain, so I'll not explain this. Appearance of Zariski's main theorem is not surprising, because if you look at a standard étal morphism in its original form, Ax localized at G modulo F, it comes with a natural compactification, because Ax mod F is finite. If you rewrite it as Axy upon F and y times F prime minus 1, then the compactification is not obvious. So in the inverse function theorem of the étal kind that we wrote, compactification is not obvious. But in standard étal, the compactification is obvious. And without that kind of compactification, you cannot apply Nakayama lemma. Nakayama lemma all the time needs finite modules. And so it's not surprising that Zariski's main theorem is needed. So after all, if you have that result, then locally you have Zariski's main theorem. Namely, just take Ax mod F, and that is the compactification of this quasi-affine thing. So, okay, I won't say more about this. This is Zariski's main theorem in its algebraic form, and that goes into the proof of this. So applying Rosetta's stone requires a lot of work. Yeah. But then you have it. Oh. Yeah, I mean, no, not without Noetherian, I don't have proof. No. But or rather, I reduce the non-Noetherian case to Jesus. See, if you're talking of proof of what? Without Noetherian, the proof is there by Peskin. No, I think Grothendieck, Grothendieck requires too many assumptions. Excellent rings and all kinds of things are needed in Grothendieck. Yeah. So Grothendieck is too much. The proof in EGA is no. I mean, frankly, I have not digested the proof in EGA. It's too difficult for me to digest. So I have read Peskin's proof in all detail. That's the one I lectured on in IIT. Okay, back here now. Let's prove étal star equivalent to étal FU. So étal star implies smooth, star implies flat, as we just proved using Jesus and Noetherian reduction. Étal star is of course unramified, so this direction is done. Now for the opposite direction, I'll give you a sketch in the Noetherian case. Okay. So if it is writable like this, then then because the relative differentials are 0, there are some of these which generate I mod I square, the right number. Okay, because if I take this, then in the Kähler sequence, the middle term is going to be free module. the differentials of a polynomial ring are free. The middle thing is a free module. And because of the section, it's going to split. And so I mod I square is going to be again locally free. And so yeah. So it's a question of finding the right number of generators, because I don't know whether this is generated by the right number of generators. So I take those generators which differentially are right, which generate I mod I square, and try to show that they do the job. And that can be done through a base change and base change to a certain point and using what is called as fiber-wise criterion for flatness. That's how the proof will go. Fiber-wise criterion of flatness, etc. All these things are standard lore of commutative algebra, wherever they have big chapter on flatness, all such theorems are free. On the other hand, if you use that big Rosetta Stone theorem, then you can prove that anything which is étal in either sense, étal fu or étal star, is locally standard étal. So standard étal equivalent to étal star equivalent to étal fu with the Rosetta Stone as the in between, which is obviously both. And both can be reduced to this using Zariski's main theorem. And because I already told you that using Zariski's main theorem, one can show that the unramified are closed subschemes of standard étal. Now, the last step involves the splitting of some sequence, which is already split. It has to remain split after a certain specialization. Étal fu means flat, and so tensoring with flat preserves exactness. And étal star is going to preserve exactness by this kind of fictionality. It is going to again split. So both of them are okay. And so there's a threefold translation. This is étal star, means it is Zariski locally standard étal, which means étal fu. The historical Rosetta Stone was a three-way translation, and the middle thing was Greek, and on one side was some Egyptian hieroglyphics, whatever. On the other side was something else, and it is the Greek part of the text which allowed them to go from here to there. So that's why I named it Rosetta Stone. The three things, one of them very understandable, but then you use it to go back and okay. So this was the older proof before Condé-Lagoux and Noethern reduction. Now, here I have summarized the flatness criterion. Clearly, I don't have too much time to show you all this. So let me zip through that and then come to smoothness. So smoothness has three versions. Étal had two, this has three. First version is smooth star, means it's formally smooth, and all these are assumed to be locally finitely presented, plus formally smooth is smooth star. Smooth polyétal, these are names I invented as pegs on which to hang my memory. Otherwise, that smooth and that. And afterwards, all these pegs are removed and it's just smooth. So this polyétal means locally it has a factorization. This goes as an étal morphism into something affine followed by the projection of the affine. It can locally factorize, and you will see this as the definition of smooth in many places. Perhaps even Kleinman, yes, certainly. Altman Kleinman has definition. Maybe SGA1 also has some of these older definitions. EGA might have some of the older definitions, but this kind of definition is very common. And I never liked it. Yes, I never liked it, though algebraically it's very nice to deal with. And you can even show it composes by completing some square, and because you want a single étal and a single polynomial. So if you compose two, you will have to do a base change and put it in that form. Not difficult. So that is smooth polyétal, and the last definition, which I call smooth flat differentials and dimension. There are three conditions there. It's a flat morphism. The Kähler differentials are locally free, and their rank anywhere is the fiber dimension at that point. Three conditions. They sound weird, And they're obviously satisfied by this. They are obviously local. You only have to check them locally. But what does it functorially mean? And how do you compose them? And so on. Composition is not very difficult with this, but not obvious again. So these are the three definitions. I have written here a proof that in the Noetherian case, they are all equal, using the usual jugglery of local criterion for flatness, fiber-wise criterion for flatness, using things like if I have some ring, Noetherian ring, and I go model an ideal, and that quotient is flat, then that ideal has to be principal, and then this quotient is open. This requires the ideal to be finitely generated. That's where Noetherian comes in. Otherwise, this is false. Okay. So all such things go into proving it in the Noetherian case, some equivalence. But still, I must say, going the last step in general, that for non-Noetherian, going from smooth FDD to smooth star, I am unable to do without the Rosetta Stone. Because I cannot, it must be true, because after all these are equivalent using Zariski's main theorem. And therefore, there must be a Noetherian reduction for the smooth FDD kind of homomorphisms, but I cannot generate one directly. If I could generate a smooth FDD Noetherian reduction directly, then I would have completely bypassed Zariski's main theorem in this lecture. So as I was preparing this lecture, I thought very hard for about 3-4 weeks on this, trying to reduce directly. And so my question to the experts in the audience, do you see a way of direct Noetherian reduction, no Zariski's main theorem, no associated jugglery, which shows that FDD homomorphism will come from a base change of an FDD finite type morphism of Noetherian rings. If you can do that, then big chunk again gets simplified. Okay, so now let me go on. Now, so one user, so all this is setting up étale and smooth morphisms, but what does one do with them? So I began with saying that étale and smooth morphisms come up in setting up spaces themselves. And I want to talk a bit about it to the younger audience because this gives a direction to what one really needs to study at that age. If you want to go into these subjects, of course, mathematics has so many interesting things and there's no single answer to what should be doing. But if you want to follow moduli theory more seriously, what's the kind of thing you do? So here's something very surprising. I invented an example of this, but later I found the examples in the literature. The very example I discovered was there in 1968, Bombay Colloquium of Michael Artin. So okay, I'll show you what is that example. So first, let me say, you can talk of equivalence relations on schemes, in fact, on any category in which this product is there. You don't even need the product, then you just take two morphisms. So that's a morphism such that on any valued points, you get an equivalence relation on the set of valued points. And this map should be injective. This map should be injective and its image should be an equivalence relation on the set A. Then you say this is an equivalence relation in schemes. Completely functorial definition of an equivalence relation. So for example, if I take, I know already there is a scheme Q, I take an open curve, I take its disjoint union, and I take the disjoint union of the overlaps. And then that is an equivalence relation because the overlaps go in this way or that way. Overlap can be of that same open set with itself that will give you the diagonal of the equivalence relation. It's obviously transitive, etc. And the quotient is going to be Q. Of course, here you can ask, what exactly do you mean by quotient? If you already know schemes, then you can say it's a schematic quotient in schemes. But if you are trying to set up schemes and you begin with affine schemes UI, and then you'll have to do a bootstrap, because if you begin with affine schemes, the intersections are not going to be affine unless they are separated. So you first begin with affine schemes, then bootstrap to get separated schemes, and then bootstrap to get schemes. You'll have to do it in 2 steps. Assume separated for simplicity, these are affine. Then using affine schemes, I can set up schemes as such quotients, but I cannot say quotients in schemes. So I'll have to take those quotients in some topos best idea to simplify my lecture is to take the FPPS topos. Ethyl topos will also do here. Gaussian topos will also do. So you take the quotients, set valued sheaves in the FPPS topos or all affine schemes, and then the quotient will be Q. But here's the surprise. If I begin with a scheme and I set up an equivalence relation on it, so that those maps to x-axis and y-axis, R to x and R to x, source and target maps as they are called, they are locally Zariski open embeddings, suppose. Will the quotient be a scheme? And it need not be. So I'll tell you the example I discovered. To me, caused great deal of shock. And I tried hard to prove it's a scheme and then prove it's not a scheme. So here's my equivalence relation, or I should say Michael-Artin's equivalence relation. I found it in this. So you take an affine line, and on the affine line, I have to give you the equivalence relation. So my x is going to be A1. My R is going to be 1A1, which is the diagonal, and let me take it over C, all I need is characteristic not equal to 2. And I'll take its disjoint union with punctured A1. So whatever you might call it. It doesn't play any role as a group, but since it has a ready-made name, I have used it. And the equivalence relation looks like this. So this is x cross x. This is the diagonal. And this is the anti-diagonal. And so this R is mapping to, I have two maps, one this way and one that way, are mapping into A1 cross A1. It's not a close-up scheme there. But at the level of functor of points, it's always giving an equivalence relation on the functor of points. Go modulo this equivalence relation, which is Zariski open embedding anyway. And it's not a scheme. So, you hear things like you have Ethyl equivalence relations on schemes, and you want quotients, you get algebraic spaces. No, even Zariski equivalence relations give algebraic spaces and don't always give schemes. So, where are we? So if I have equivalence relation schemes such that projections are Zariski locally open embeddings, then these are not necessarily schemes. So algebraic spaces were introduced as quotients. So because formal ethyl, what is missing is an implicit function theorem. You want to create local neighborhoods, and you cannot, because you cannot choose something in X and then it gets identified with something by going to R. You cannot do all that. And so, but formal ethalness is like inverse function theorem. So you should be using that to create atlases. And so Artin introduced that. Artin took ethyl equivalence relations, which means both these projections are ethyl, and introduced the FPPF quotients in the FPPS topos are algebraic spaces. Now, this is where I learned another very important piece of my knowledge from Kapil. Pay attention. This was in 1993, probably. Were you then back from your postdoc and you had learned some very interesting thing, perhaps, or you had figured it out yourself? One day you told me, one afternoon after lunch, he told me about representability of schematic representability of morphisms, or algebraic space representability of morphisms. Representability of the diagonal. This phrase I first heard from you, and it immediately struck me as extremely important. And really, thank you very much. So this is one of the things that any number of things which I have learned from Kapil through his stray remarks on different occasions. So the problem is how to do algebraic geometry with such quotients, because after all, you want to locally do some commutative algebra, prove your things, have properties of morphisms, properties of spaces themselves. You want to apply them to such quotients. These are, to begin with, only sheaves of sets in some FPPF topology. The answer to that is called representability of diagonal. And representability of diagonal can be proved only by using Zariski's main theorem. So one of my takeaways from the revisit is the massive importance of Zariski's main theorem for proving all the foundational things in algebraic geometry. Here, the way Zariski's main theorem is used is to show representability of diagonal, you have to create finally some scheme. This scheme you can create somewhere else as a quasi-affine morphism. Quasi-affineness is proved using Zariski's main theorem. And effective faithfully flat descent holds for affine morphisms, that's Grothendieck's theorem. And therefore, via Zariski's main theorem for quasi-affine morphisms, effectivity of descent holds. This creates the scheme which represents the diagonal. This is the answer. Now, till when am I up to lecture? -5 minutes? Oh, really? Then I'll rapidly show my last slide. Okay. So this is more about algebraic spaces as quotients. There's some more magic which takes place with étale morphisms. Now that we have set up étale and smooth morphisms, the funny thing is if you have flat equivalence relations, their quotients are again algebraic spaces. So there is a way of approaching flat morphisms via étale morphisms. And this is really magic, and it occurs in two different very foundational places in mathematics. One is the theorem of Artin, 1969, and in 74 again another proof of how to get étale curves when all that you have is some flat equivalence relation. Another is the so-called Kiel-Mori theorem, where again you can construct quotients which are algebraic spaces, though to begin with these are only flat equivalence relations. So here are the takeaways from revisit. Important to have both functorial and algebraic points of view. And to effectively deploy étale and smooth, one needs the technology of flatness, regular sequence, LCI morphisms, and you have to use the cotangent complex. I have no time to tell you how that is effectively used. Noetherian case, everything gets a shortcut via Kondolabu, as I have seen. So compare how I am doing it with standard textbook treatments. You will see what simplification is achieved. But needs all the powerful machinery about flatness. That's no alternative to that. And Zariski's main theorem plays a very important role. Standard étale allows you to go back and forth between things and a bit of look ahead. So Artin used all this, then his approximation, deformation theory, to characterize algebraic spaces and algebraic stacks purely functorially, and deformation theory then becomes the main thing for such characterizations. So what I was first saying is schemes don't have good functorial characterization. Algebraic spaces and algebraic stacks do have. And that's very important for moduli theory, because you begin with your moduli problem as a functor, as Kapil's then favorite article titled Moduli Problem. So there you can begin. And so there's no time to tell this story. There's yet another thing how to go from there to good old-fashioned algebraic spaces from some stacks. That's the theory of good moduli. This is the latest hot thing in the subject. So more about it on some suitable future occasion. Thank you.
Any questions or comments?
Yeah. Dinker is waiting. Yes. Yeah. Yes. That's why I did this only in the Noetherian case. Kondolagu, not me. This is Kondolagu's proof in the Noetherian case using completions. I did the reduction to Noetherian. So I can apply this. Flatness remains flat under base change. No? So if I can preserve, if I can do a reduction and preserve smooth star, formal smoothness, then do all this Atiyah, MacDonald, flatness of completion, and then base change back. Yeah. Yeah, without Noetherian. Yeah, this is Peskin's proof. Reynaud doesn't refer to Peskin, but that is Peskin's proof. Or maybe he gives the reference. And Reynaud's treatment is very fast. First, I tried reading Reynaud, didn't follow everything nitty-gritty. Peskin gives longer account, but being retired and not having access to any library, I couldn't have in my hand Peskin's bulletin 1967. It's too old to have been put on archive and or in any electronic form. But I found Peskin has a textbook called Complex Projective Geometry, and there he has given the proof in terrible notation, but it's all there.
Any further comments?
Not a neat definition. I can give you a definition if you want one. The kind of bootstrap definition which I created first. So it will involve saying that there exists some affine schemes, collection of affine schemes, anamorphism, which is locally Zariski open embedding, which can be functorially characterized, and which is surjective in the FPPF topos. Epimorphism there. And plus representability of diagonal. And usually all this works well, and I have not said it, when you also build in quasi-compactness. Otherwise, direct image of coherence goes for a toss. So you have to build in some hypothesis. It can be done, but it's completely awkward and uncheckable. You are given a moduli functor. See, how do you create a candidate atlas? That's the problem. If you can imagine an atlas, and if you have the right intuition, proving it is indeed the atlas is not so difficult. Question is, where do you get one from? Now, in the traditional moduli theory, the atlas comes from the construction of a Pope scheme. That's again the main thing of thinking. FGA, what he did was he constructed Hilbert and Pope schemes. And then that provided atlases for all kinds. Versal kind. But Kapil, be careful. And I have had no time to say such things. But here my rings C or C prime are any rings. One can ask whether one can take finite ones, Artin ones, around a certain point of interest. And that is what is called versality. Versality is a word which comes from deformation theory, where these are Artin local rings now. And that is adequate in a Noetherian situation. That again requires.
Okay. Anything else? Yeah, welcome back. So our next speaker is Professor Ramanan from CMI, and he will be speaking on geometry of orbit and hyperelliptic.
It's on, right? Happy birthday to you. I want to say also, I have great pleasure. I'm happy to greet you on this occasion. So the happy birthday happiness is not only for you, the happiness is for all of us to be here on this occasion. So I'll make my talk one short because this is the last talk on the last day. So I'll make it short. And secondly, I'll give you no proof. If there is anything, I will say it can be proved. Okay? So believe me. And thirdly, I will give a talk on in here, right? Geometric aspects of certain varieties, certain algebraic varieties. Okay, which is appropriate for the title of the whole conference. Okay. Madam?
Put this in the talk.
What is it? Okay. Better. Okay, it will be geometry of quadrics and hyperelliptic curves. And first I'll start with the geometry of curves. That's why I put it first in the list. So I'll mostly stick to the complex field. Everything will be over complex numbers. You can imagine so, but I'll present it in such a way that it will be valid over any field of characteristic 0. In particular, number fields. Now, I am a geometer, although I have written a few papers in geometry over any field, the number theoretic interest. I am basically a geometer, therefore, I like complex numbers more than any other field. But why do I do this? Actually, the results which I say go back to the 60s and 70s, some of them. And as I said, I have rephrased it so that it will work for any field, any number field, which is not necessarily algebraically closed. And there are also a few new results pertaining to the old the old results. Why was it done? It was done because Jaya Iyer, one of my students, and Parimala Iyer, one of my ex-colleagues, and say quasi-student, they wanted to prove Hasse principle. Hasse principle means it is related to so-called Brouwer group or any field. So in any field, Brouwer group is the one which measures why a simple algebra is not a matrix algebra. So that measure is constructed as a group. It has a group structure, and that is called the Brouwer group. And associated to the Brouwer group, there are two numbers, and whether there is a conjecture regarding those. It's called period and it's called index. It's called a period index problem. So for the period index problem, for which algebra, which is the functional algebra of a hyperelliptical. So they wanted to study that. And in order to do that, they had to have the old results, the geometric results over a field. So I began to think about the old results, which go back half a century, in which I was involved at that time. So I had to rethink most of those ideas. So that was about a few months ago. So I thought that would be a good topic to present here. So let me start with just P1. There is no difficulty, but I'll be even in the Tata Institute, some students used to call me a categorical man. So everything has to be done a little categorical. That is, don't choose basis, no, that kind of thing. Pardon?
That once every number is integer, is positive integer is the dimension of vector space. Every positive integer.
Yes. Every positive integer. He said, I once mentioned that every positive integer is a dimension of a vector space. So So I was a passionate admirer of Bourbaki, Grothendieck and stuff. So, but then it doesn't mean that I stick to it all the time. For example, occasionally you have to do things. Sometimes I do take a basis, but So, sorry. U is a two-dimensional vector space. We will take a two-dimensional vector space because PU is P1. So projective line, instead of saying projective line, I will say take a two-dimensional vector space and take PU. And then instead of saying take a 2G plus 2 dimensional, 2G plus 2 degree homogeneous polynomial of degree 2G plus 2 in two variables. Instead of saying that, I say gamma P O 2G plus 2. So which is, of course, S of 2G plus 2 of U star. Okay. No, I'll be elementary. Don't be annoyed by what I'm saying just now. So, so this polynomial has zeros, 2G plus 2 zeros. I am assuming they are distinct. As I said, although I'll present things over any field, often I'll do it for complex numbers here because that will be easy to understand. So there are 2G plus 2 points in P1, if you like. Of course, if you have x squared plus y squared as a polynomial, it doesn't have a 0 over R. Okay. So it doesn't, 2G plus 2 points are not over K. So the polynomial is over K. Any linear form on gamma D O2G. What is D? D is the zeros. The divisor given by the zeros. That means 2G plus 2 points. So take gamma D O2G restricted to D. Okay. This, any linear form on this gives us a quadratic form on V. What is V? V is gamma D O2 OG. See, D is a few points. So gamma D OG is essentially 2G plus 2 vector space with a basis. Okay. But as I said, for any K, there may not be a basis. Okay, that is why it's right gamma D OG rather than saying summation of so many 2G dimensional vector space. You may think of it as 2G dimensional vector space. 2G plus 2 dimensional vector space. Sorry, it's a D is the polynomial sigma has degree 2G plus 2, therefore there are 2G plus 2 zeros. Therefore, this vector space is actually a 2G plus 2 dimensional vector space. But I want taking particularly gamma D OG. Now I am saying there is a natural map of gamma G. Where do they go? There is a natural map from gamma G, gamma DOG to gamma DO2G. This means that if you have a basis, you will take sigma xi to xi squared. x1 etc. x2g plus 2 goes to x1 squared, x2 squared, x2g plus 2 squared. Okay. This is a fancy way of saying gamma DOG to gamma DO2G. Okay. And then if you take a linear form of the gamma O2G, then it becomes, and you compose it with this, you get a sigma lambda A xx squared. So a quadratic form on C2G plus 2 field. How do we go back? Now, you remember V is gamma D O G. So, gamma O G to gamma O to G, there is a natural map which I said. So, gamma O to G D, D O to G is on the right, and you have an exact sequence like this. Because we had a section of O to G plus 2, which you can think of it as a map from O minus 2 to O to G. And then this, because D is a divisor of degree 2G plus 2, you have this exact sequence. Now you take the homology sequence for this. In particular, so gamma O minus 2 is 0 because it's a negative degree. There is no section. So gamma PO2G is in the middle. Sorry. This gamma O2G and gamma DO2G. And then you have H1 O minus 2. H1 O minus 2 is the canonical bundle on the projective line. Therefore, H1 O minus 2 is complex numbers. So you have this exact sequence. So, as I said, any linear form on gamma D O to G gives a quadratic form. Again, I repeat, it is from gamma D O G to gamma D O to G, squaring everything. And then you take this linear form. So you get something like sigma lambda xi squared. And this is absolutely canonical. I've already asked you to excuse me for being canonical. So, dually, you can say C is contained gamma D O to G star. This is just the dual of that sequence. And therefore, you have, as I said, a canonical linear form of gamma D O to G. Therefore, there is, I gave you on gamma D O G, there is a God-given quadratic form. No, any element of gamma. Now I will go back and see. Suppose I take an element of gamma PO to G. That's one-dimensional space of gamma PO to G star. That's a linear form on gamma PO to G. Then you can take the inverse image in gamma DO to G star. Is it clear? Take a one-dimensional space here and take the inverse image. You get a two-dimensional space here. Okay? And therefore, you'll get two-dimensional space of quadratics. Because any linear form on gamma DO to G is going to give you a quadratic form. So you have two-dimensional subspace of these linear forms. Therefore, you have two-dimensional subspace of quadratic forms, of which the canonical one is one of them. Okay. So that's what I have. Any element of gamma PO to G star gives thus a two-dimensional subspace of diagonal quadratics. Diagonal, if you are over C and you take the basis for gamma OG, then these are all like sigma lambda xi squared. If you like, you can think of it, the canonical form as sigma xi squared. So there's one fancy way of writing sigma xi squared, sigma lambda xi squared. And these are the basis of the two-dimensional space of quadratics. Okay? Now, a two-dimensional space of quadratics in a vector space is called a pencil. And if one of them is non-degenerate, our canonical quadratic form can be checked to be non-degenerate. As I said, I will not give any proof, but it is easy to prove. And such a thing is called a pencil, and this is a generic pencil in the sense if one quadratic form is non-degenerate, almost all of them are going to be non-degenerate. So it's called a generic pencil, and they are also diagonal pencils in the sense that if you go to the algebraic closure, they will be actually diagonal. So, but when I mean diagonal pencils, when I say diagonal pencils here, I mean that not merely diagonal pencils, but I am saying one of the quadratics in the pencil should be the canonical quadratic form, which I gave you right to the beginning. Now, in particular, whenever you have an ample line bundle, you can embed the variety in the ample line bundle, projective line bundle, these sections. So, in particular, P, the projective line, is embedded in P gamma D O2 G star. Okay? All right. So, for every element P in P, you get a line for you get a linear form gamma P O2 G. This is what is called the rational normal curve of degree 2G. You embed P1 as a conic, as a twisted cubic, and so on. And in particular for 2G, you can embed it as a 2G degree rational normal curve. That's did I make a mistake? Yeah, that should be P. Sorry. No, that's why there is question mark. Yes, I understand. And I don't know how to erase it from here. So now I sum up. I started with a sigma, which is a 2G plus 2 degree polynomial. And I gave a vector space of dimension 2G plus 2, which was gamma D O2G, OG, if you like. I gave a canonical non-degenerate quadratic form on P, which I called, which I'll call Q. And a family of pencils parameterized by points of P. Because for each point of P, I got a two-dimensional space by taking some inverse image. And so I got a pencil. So every point of the rational normal curve of degree 2G plus 2 gives a pencil. Okay. So this is the first part. This is the geometry a little bit. I'll come back to some more geometry afterwards. So, I'll study what I'm going to study on these quadratic spaces. So start with the quadratic space. I suppose everybody will know it, but I'll recall. If VQ is a quadratic space, that means a vector space with a non-degenerate quadratic form. Then any space to which, any subspace to which the quadratic form restricts to 0 is called an isotropic subspace. This means that subspace correspondingly in the quadric is contained in the quadric because Q equals 0 on that subspace. So the subspace ID of d-dimensional, I'll denote d-dimensional isotropic spaces from a variety It is contained in the Grassmannian of D-dimensional varieties. Namely, the subspaces on which Q restricts to 0. So that is, I denote that variety as ID. If D is greater than or equal to total dimension is 2G plus 2. I am not saying 2n, but 2G plus 2. And if D is greater than G plus 1, it's empty. There is no isotropic space of more than half the dimension. Total is 2G plus 2, half is G plus 1. If it is greater than G plus 1, there is no isotropic space. But if it is in isotropic space less than G plus 1, if you take all the isotropic spaces of degree D less than G plus 1, then it is an irreducible variety. But how about D equals G plus 1? That is left out. If D is greater than G plus 1, there is none. If D is less than G plus 1, it's an irreducible variety. But if D is equal to G plus 1, it has two components, two irreducible components. In fact, they are also non-connected, that is, two connected components, not merely two irreducible. So now the Grassmannian is embedded in P lambda G plus 1 as taking the determinant of for each bundle. So in particular, I is also embedded in P lambda G plus 1 B. Lambda G plus 1 is a G plus 1 exterior power, and it's embedded in the projective space of that. This gives rise to an ample line bundle on I. Namely, this embedding and pull back the hyperplane divisor, you get an ample line bundle. This is the line bundle, as I said, which associate to a subspace. The dual of it determined. You have to be a little loud because I don't hear it.
Yeah, just to remark that if you want to pick a component, you probably have to extend the ground.
Extend?
Like quadratic extension you require, like
Yeah,
two components.
that's two components. Two. Yeah, I don't want to keep going to technicalities. Yeah. Actually, this bundle, this determinant bundle and its dual, when you restrict to on the Grassmannian, it generates the Picard. So every ample line bundle, or in fact every line bundle, will be a power of this particular line bundle. But however, if you restrict to the isotropic bundle, this bundle is a square of another bundle. I repeat, you take the Grassmannian, embed it in the usual lambda G plus 1. So it will get an ample line bundle. That means generator of this of its Picard group. And but when you restrict that line bundle to the isotropic variety, it becomes a square of another line bundle. And the square root is called the Pfaffian. Pfaffian line bundle on IG plus 1. This happens for G. Pardon? I plus. There are two. Yeah. I have written it somewhere here. Two, in the latter case, we will fix one component and call it I. Okay. We can use both, but for expositional purposes, I take one. Now, the special orthogonal group acts on all the isotropic spaces because it preserves the quadratic form Therefore, if one is isotropic, the transform will also be isotropic for that quadratic. If you take the orthogonal group of that quadratic form, and I take the special orthogonal group, therefore, it will also this component will be also left invariant. So SOQ will operate not merely in non-orthogonality, but also in I. I is a one fixed component of the middle dimensional isotropic variant. And moreover, if you take SOQ, any element of SOQ, and try to pull the Faffian, you will get the Faffian. Because it is the square root of the same thing, there is only one square root, so it will be preserved. However, it does not lift to that. It does not lift to the Faffian. That means you can use the isomorphism and lift it. But if you do it for one element X, another element Y, and you have also lifted for XY, then they will differ by minus. So plus or minus. Therefore, although the pullback of the Faffian is Faffian, for every X in SOQ, it does not lift as a group to the line bar. However, there is a two-sheeted covering exactly using this equivalent. You can give of the SOQ, which is called the spin Q. The spin Q group acts by definition on this Faffian. So it will also act therefore on the sections of the Faffian because it lifts to Faffian. If you had only SOQ, it will only projectively lift. So, which is also interesting. This so the spin Q is operating on gamma Faffian, and that representation. So it's a representation of the spin Q. That's called the half spin representation. It's irreducible, and it's called the half spin representation. If you do it on the other component, which I called I prime, you will get the other half spin representation. So together it will be a spin representation. Okay. In particular, we are in the diagonal situation. So you take the diagonal elements of the orthogonal group. This will be plus or minus 1 everywhere. If you take SOQ, of course, the product, the number of minuses will be even. And you can take the inverse image of that will also have the same property as element. Every element has the SOQ, pulls back Faffian to Faffian. Therefore, this finite group will also do that, but it will not even extend in that case. But its inverse image in spin Q will lift that. And will also act, therefore, on gamma PF. But it's only a finite group. It's a central extension of this group. And still, it's irreducible. Yes? I don't know. I don't know. So given sigma, so again, I sum up. Given sigma, no, this is something else. So that's about the geometric aspects. Now of the algebraic variety. What is variety? That's what I'm going to say. So we are starting with P and with sigma. Then there is this gives rise to a projective non-singular curve X with a surjective morphism X to P, which is two-sheeted. A Galois involution I of X such as the constant is P. It's a two-sheeted curve of P. And a line bundle H on X, which is the pullback of the hyperplane bundle on P, which I call H. So those three things are already defined by sigma. These are geometric things that the sigma gives. Sigma gave a lot of geometry earlier, quadratic geometry. Now it gives hyperelliptic curves. This X is hyperelliptic curve. So you have a map, two-sheeted map from X to P, and it is exactly ramified at the points of the zeros of sigma, which is D. Upstairs, therefore, it will have only 1 point. Every point has 2 points, but these are the points which have only 1 point. So there will be the bijective. The map pi will be bijective on this. But if I look at it at W as in X, I will call it W. If it is in P, I will call it D. And the W is called the Weierstrass divisor. Now, in terms of H, we can describe the divisor W, which is H power G plus 1, which is 2G plus 2 degree. So it will be that. And H is of degree 2. It's the inverse image of the hyperplane bundle. It's two-sheeted. Therefore, H is of degree 2. So H power G minus 1 is G plus 1 is of degree 2G plus 2. And that will be the Weierstrass divisor. And the canonical bundle is H power G minus 1. Again, you can check by finding the differential of pi. You can compute. Technically, if you want purely algebraic geometry, if you want to describe, you can say it's a spec of O plus O minus D plus 1. And this is O algebra. O is already in algebra. O acts on O minus D plus 1. Therefore, you know how to multiply something in O and something in O minus D plus 1. But if you have two things in O minus D plus 1, if you multiply it, go to O minus 2G plus 2. But you can apply sigma to come back to O. So it is like saying take x squared minus f. Anyway, take I'll repeat it anyway. You take kx, and then you take x squared minus f. So that is the extension kind of thing. And those will be the fibers. And if f is 0, naturally there will be only 1 point. 1 point square. What is spectrum? I don't know. And by the way, line bundles on degree on X, they are all classified by a positive variety of dimension G called the Jacobian. And in G minus 1, there is a canonical divisor. Namely, those line bundles, if you do Riemann-Roch theorem, any element of the Jacobian will have D plus 1 minus G. D is G minus 1. So it will become 0. The Euler characteristic of any line bundle of degree G minus 1 is 0. So we do not know if this is H0 minus H1. So we do not know whether H0 is 0 or not. But those for which H0 is non-zero will be a divisor. And that divisor is called the theta divisor. So as I said, the geometrical aspects I said, now I'm going to the algebraic variety. The algebraic geometry. So take the natural morphism, Jg cross X. X itself, every point is a divisor of degree 1. This is of degree G. So you can subtract psi X goes to psi times O minus X. So you have a map from JG cross X to JG minus 1. Okay. And then you pull back the theta line bundle. You get a line bundle on JG cross X. I repeat, you have a map from JG cross X to JG minus 1. And in JG minus 1, there is a canonical theta divisor. Pull it back. So you get a line bundle on what happened? Got canonically switched off. Anyway, my lecture will be, the rest of the lecture will be to connect the two things. One is you have a, given a sigma, I have associated a quadratic space with the pencils and so on. On the other hand, it also gives a curve, which is called the hyperelliptic curve, a hyperelliptic curve. And this hyperelliptic curve, you take algebraic geometric aspects of this and relate it to that. So, for example, I said Jacobian exists. So, can you give this quadratic space with this pencil? Can you give a Jacobian? And say these two are isomorphic, and so on. So, that is the kind of results which I am going to talk about.
You have the file with you also, right? Of that laptop.
Yes. I also have the laptop. If your laptop doesn't work, I can give you. And that has Kapil.pdf. Ramanan is there upstairs. Oh. No, there is no quick way of going there, right? I have to go one by one. I don't mind either way. Even for this reason, if I take extra time, nobody else is going to be affected. Unless you have a flight. Pardon? Yeah, it is there. Oh. Yahoo. No, that's all right. You will correct it. But what happened? You will let me know afterwards. Yeah. Yeah, as I said, I took the natural map JG cross X, taking psi minus X, and restricted the theta divisor, pulled back the theta divisor. So I got a line bundle on JG cross X. And what property does it have? Hmm. Yeah, pull back the theta divisor, we get a line bundle on JG cross X. And this has the property to restrict to psi cross X. So on the for every psi in JG, you get a line bundle by restriction on X. And this is isomorphic to psi, the point at which you restricted it. Such a bundle is called, it's a universal bundle, it's called a Poincare bundle. So you have a bundle on JG cross X with a line bundle on JG cross X with the property that if you restrict to psi cross X, it will give the line bundle psi. So this is a absolutely canonical Poincare bundle. So if you take L squared, it will give for every side psi squared. It's a Poincare bundle square. This implies now you take the direct image of L square on JG. What does it give? For every psi, it gives H naught psi squared, H naught of X psi squared. Is that clear? For every psi, when you restrict to X, you get psi square. The original Poincare bundle gave you psi. I took square. Therefore, for every psi, it will give psi square. Now, if you take the direct image, you will get H naught of psi square. So, I got a vector bundle now on JG, which for every psi, the fiber, the vector space in the vector bundle is H naught psi squared. No, H naught psi squared dimension doesn't change. That's why it's a vector bundle. Because what is the degree of psi square? Psi is of degree g. This is a degree 2g. It's greater than k. K is 2g minus 2. K's degree is 2g minus 2. It's h to the power g minus 1. So its degree is 2g minus 2. 2g is greater than 2g minus 2, as you will all admit. therefore it is given by Riemann-Roch theorem. And 2g plus 1 minus g is g plus 1. So the g is a vector bundle of rank g plus 1. On the other hand, you can also take L tensor I star L, 1 cross I star L. That will give you for every point psi tensor I star psi. Because L will give for every point psi. I star L will give you I star psi. Therefore, psi tensor I star psi. You can check that for every line bundle, psi tensor I star psi is h power g. Therefore, this bundle, unlike L square, for every psi, it will give you h power g, the same thing. Because if whatever bundle you take psi tensor I star psi is h power g. Therefore, you will get h power g, and you can see that there will be a line value on this. That's not very important, so don't worry about too much. So you get h power g for every psi. Now, what I'm going to do is now I took two bundles, L squared 1 and L tensor I star L. Both of them, when you restrict to W, it will give the same because I acts as W is the I fixed divisor. Therefore, both of them will restrict to the same line bundle on W. Okay? W is only a final few points, but I'm giving you the status of a scheme. So it's a zero dimensional scheme over K, where K is a number field, let's say. But forget it, think of it as C. So both of them give the same thing on W. This gives you, but when you take the direct sum and so what I want to say is, so the vector space, if you restrict P star of L square and P star of L tensor I star L, both of them there on W will give you gamma W is power G by restriction of gamma C H power G to gamma C H power G. So both of them will give you the same thing. Therefore, you take for every psi gamma psi square and restrict to W. Now it will go into gamma W H power G. Gamma W H power G is 2G plus 2 dimensional. This is G plus 1 dimensional. So I have given you for every psi a G plus 1 dimensional subspace of a 2G plus 2 dimensional, my V. That's what I've written here. For every psi in JG, you have a map of gamma. There's only a restriction map. You can check it's injective. But because the kernel, when you restrict psi squared to W, the kernel will be psi squared tensor O minus W, which is 2G plus 2. This is only 2G, it's negative. Therefore, gamma is 0. The kernel is 0. Therefore, it's injective. So I have given you an injective map of gamma psi squared to my vector space V. And then you check that the image, it's not difficult, to check that this is isotropic. So that's what I have given. Why it is. So let's accept this. I have given the reason, but I don't want to go into the detail because I don't have too much time. I thought it'll have finished in half an hour, but I think I'm talking too much. So thus we have a map from JG to G plus 1 dimensional isotropic variety in V. Because I take any psi, I take H naught X psi square, restrict to W, and interpret gamma W psi squared as gamma W psi tensor I star psi, which is H power G, so which does not depend on the particular psi. Therefore, you go to the same vector space B. So I have given you, and I proved that it's injective. You can also check fairly easily that it is isotropic for the canonical quadratic thing. I had given the proof here, but I didn't want to spend time on that. So what have I done now? Now I have related the algebraic geometry to the geometry of quadrics. Namely, I took the hyperelliptic curve given by sigma, and then took its Jacobian for degree G, which is JG, and gave a map into the isotropic space I, maximal isotropic space I of the quadric space, which I associated canonically. So I have given a map, and that's injective. One can show that he is injective. And therefore, to further, you have taken a maximal isotropic space and you would like to know what is this. First of all, this map is not injected from JG to the isotropic space, because you can easily check from what I have said. The evolution acts on JG, because every line bundle of degree G, I star psi is also of degree G. Therefore, I acts on JG, pass to the quotient. JG over I is embedded in I. JG over iota is embedded in I. And we would like to know what is the image. Okay. So what I'll do is, I'll take the pencil. So you'll remember, I not merely gave a quadrant. So far, I have used only the quadrant, but I also gave pencils. For every x in P, every P in P, I gave you a pencil. So use the pencil to define what is the image. Yes, that bracket doesn't have a companion. Please excuse me. If you take a general pencil, there is no G plus one dimensional spaces contained in both the quadrics. So it cannot be, I cannot describe it as subspaces which are isotropic for all quadrics of the pencil, because there is no such thing. To every P, I have already said that we have associated pencil, and therefore will characterize the image in terms of this picture. For every x in X, the image of the hyperplane X psi square times O minus X. It's not X psi squared, it's of dimension G plus 1. This is a dimension G. It's a hyperplane there. The curve is actually embedded in gamma X squared star. Almost. As in the case of Fiji, we can also check that this is isotropic. This is isotropic for the whole pencil. Given by, I took an X. This X has also given a point on P. And point of P has given a pencil. So this is isotropic for the pencil. I repeat, take a point of X, a point X in the curve. Then you get a hyperplane gamma X psi square. Namely gamma X psi square tends to O minus X. On the other hand, X gave you a point of P. Therefore, for every P, I have given a pencil, diagonal pencil. And on that pencil, this is isotropic for all the quadrics of the pencil. After all, for one of them, it is already, because it's contained in a maximal isotropic space. It is also isotropic for the entire pencil. Okay. So in other words, the other quadric, when you restrict to the isotropic space, contains a hyperplane. How can a quadric contain a hyperplane unless it's two planes? So, so this shows that if you fix a point of P and take the corresponding pencil, on that pencil, it is isotropic total. For one of them, it's completely contained. For the rest of the quadrics, all the rest of the quadrics, therefore, will give you one quadric on this, because this particular quadric is 0. So the remaining will give you only one quadric. And that quadric becomes a pair of planes. Theorem that this is isomorphic. J over I is isomorphic to the set of isotropic maximal isotropic spaces for the canonical quadric, and to which the pencil restricts as a pair of planes. That's the theorem. That's the theorem is long ago, as I said, due to Jaya and myself. But now I have presented it in a way which is valid for over any case. They wanted it. Jaya and Parmala wanted it. I have written it here. Jaya and I prove that phi maps the variety Jg over iota to be called the Kumar variety. That's called the Kumar variety. Isomorphically of the subvariety for Ig plus 1 consisting of subspaces to which anyone, therefore all quadrics of the special. Yeah, I must say, I chose X. You could have chosen Y. All of them become a pair of planes on this coin. Okay? It is not just one pencil that becomes a pair of planes on all these, on all points of Jg over iota, but all the pencils become pair of planes on this. That's not surprising in the sense that I even said what is the plane, hyperplane to which it splits, namely gamma x psi squared tends to O minus x. And for every x, you have psi squared tends to O minus y and so on. So the whole curve is embedded more or less there. So for x pencil, it will give this hyperplane. For y pencil, it will give the hyperplane corresponding to y. X and ix, because we chose a point only in P. So there will be 2 points, x and ix. They will get identified. That's why it is Jg over iota. Isn't it beautiful? Now, I want to say something definitely new. That is the pullback of the determinant bundle. So I gave a map from Jg to maximal isotropic spaces. Variety. I. Jg to I. Now, the pullback of the determinant bundle, you can find out because you can take h naught psi squared, take the determinant and see what it is, and then see that the pullback is O minus 4 theta. This is in Jg. You may wonder on Jg minus 1 had theta, but Jg has 2 theta anyway. 2 theta is canonically as a line bundle, not as a divisor, but as a line bundle defined on all Jacobians. Therefore, the pullback is actually minus 4 theta. I computed it recently. Thus, if you take Pfaffian, I told you Pfaffian square is the determinant inverse. Therefore, pull back Pfaffian, you will get 2 theta. Pf squared will pull to 4 theta. So Pf only, there is some problem because it will give you 2 theta tensor an element of order 2. So I had some difficulty proving that, but then finally satisfied myself saying that since everything is canonical, it has to be either 2 theta or 2 theta tensor alignment of order 2. So how you cannot have an element of order 2 for all hyperelliptic curves. Therefore, that's easy to prove, and therefore that alpha should be trivial. So what is the result? The result is the pullback of the Pfaffian pullback of the Pfaffian by the map which I gave you, which I call phi. Yeah, that's what I've written. Whose square is 4 theta, therefore I have written that. So therefore, conclude that the pullback is actually 2 theta. Okay. Now Why is it interesting? Because gamma IPF is a half-spin representation. And its dimension is 2 to the G. Gamma J 2 theta, the dimension is 2 to the G. Okay, the Pfaffian pulls back 2 theta. Gamma PF is 2 to the G, which is a half-spin representation. And then gamma 2 theta is 2 to the G in the Jacobian. And there is a natural map. Okay. Now you can see that 2 to the G, the elements of order 2, the Jacobian act on that. Not quite, but an extension works on that. And that's irreducible. And you can identify it with elements of order 2 diagonal. And that is irreducible on the half-spin representation. And you can see that this map, this action and that action are compatible. Therefore, the pullback of the half-spin representation into JG2 theta is irreducible. Both representations are, both sides are representation spaces, and you check that the map that I have given is compatible with these actions. Therefore, by Shurama, it has to be an isomorphism. Both are dimension same, so it has to be an isomorphism. So what have I proved? I think it's an interesting fact that if we take JG and 2 theta the Jacobian, and take its sections on the one hand, and take the half-spin representation on the other, they are canonically isomorphic. So you see, geometry and algebraic have related. Oh, this has been done. Oh, I'm going back or going? What am I doing? Yeah, like so, I have said. Now, similarly for less than I said, this can be identified with hyperelliptic curves for the canonical quadric, which is also a pair of planes for the pencil. Now, similar theorems we also proved, Jaya and I proved, for moduli of vector bundles of rank 2. Similarly, you can give a map into the maximal isotropic spaces. And that variety will be, the pencil will have, all the quadrants of the pencil will have rank less than or equal to 4. That is what we proved, Jaya and I proved about half century ago. That again is done over a field now. Okay. There's only rearrangement of the proof so that it will work for etc. That is the only thing which I said was new. So that's what I've written. Now, in genus 2, we worked out, Narasimhan and myself did all these things in genus 2. And Miles Reed, Peter Newstead, etc., they were interested in this. I must also say that everybody knows that gamma JG 2 theta is 2 to the G. Everybody knows half-spin representation is 2 to the G. Everybody knows that there is a relation between these two. I would not be surprised if somebody had already noticed. See, I am not in touch with the current literature. I do not know whether somebody has done it or not. If somebody will write to me, it's good. I am S. Ramanan at cmi.ac.in. So if anybody knows that has been done, please let me know. before I write it up and submit it somewhere. As I said, you can do that. This is new thing, work in progress. I am Sarbesh and I now are discussing something new, which is there is a what's called a Hitchin space, where you don't take vector bundles alone, but you take vector bundles together with sections of K tensor ID, which is very interesting, but I don't want to go into it now. It's called the Hitchin space. Hitchin defined E phi. Phi is a map from E to K tensor E. This pair, E phi, he defined when it is stable, unstable, semi-stable, etc., etc. And he constructed the moduli of such pairs. Huh? You did. Okay. Sorry. I'm not sorry that you did it. So it will be interesting to know a big open set in this Hitchin space it is the cotangent module of whatever I have done, whatever I have given. Okay. So can you give a geometric interpretation of the whole Hitchin space? Is the question. We seem to have done it in genus 2. We have not checked full details. And once it works for genus 2, we would like to extend it to all genus. Work is ongoing in collaboration with Sarbesh. If it is 5:15, should I stop here or just I want to say in genus 2 what this is? As I said, 2 theta line bundles sections is 2 to the G dimensional, which is 4-dimensional. And the half-sphere representation is also 2 to the G, which is 4-dimensional. That is P3. Projectively, it is P3. And the Kumar variety is the Kumar surface there. So all the results, the geometric aspect of it was done, believe me, in the 19th century. I have written in my abstract 150 years ago. It appeared in Mathematics Annalen, Volume 2. And it is not just a history. Narasimhan and I, when we worked on genus 2, we got a lot of inspiration from that paper. And also it made me understand German better. So as I said, in this case, V is 6-dimensional, 2G plus 2. G is 2, so 2G plus 2 is 6. Okay? So that space is in P5. Q is a quadric there in P5. Actually, it is the Grassmannian in 4-dimensional space. So you can get the 4-dimensional space that way. The isotropic spaces can be identified with P4. There is no embedding of this isotropic space in the thing is actually isomorphic. That in that case, it's called a Kumar surface. That's the reason why I call JG by iota the Kumar variety, because this is a Kumar surface. It is Kumar surface is embedded in I. I is actually P3. There is a surface in P3. It's embedded as a quartic surface. Yes, I've already said it. And only one more remark. That is, you can take some diagonal pencil and asked. I said a lot of diagonal pencils I gave you for every P in P. This breaks into two planes. No, other quadrant, other pencils, quadratic pencils, which with the same property. Okay. Recently, I proved it is not. That if there is a diagonal pencil which restricts to my image of JG, all of them as pair of planes, then it must be one of the P's, one of the P in P which gives the quadratic. Okay. Now, why is it interesting? Because Klein proves in the paper that he calls what I call the pencil a quadratic complex, and he proved that only quadratic complexes which have Kumar surface as a singular locus is this. So that is generalized for any G. Its parameter, he proved its parameter is a rational quadratic curve. You remember our P is embedded as a 2G plus 2 normal curve. So everything completely generalizes. That's what I mean. Some results, similar results are also available. Not merely I said it for Jacobian, I said it for vector bubbles. I generalized it, and also Jaya generalized it. For if we take maximal isotropic spaces, which for this pencil has lower rank and things like this, how can you interpret it in terms of the curve? In terms of spin bundles. In low spin, it's vector bundle and so on. So yeah, thanks for the page.
Any questions? Comments?
Pardon?
You can also look at G equal to 1.
Yes, you can also take it. Huh?
That's there with the Riemann expression of the elliptic curve.
Elliptic curve, correct. In fact, I wanted to say, why is it called hyperelliptic? It is because the Weierstrass function, P function, maps it to P1 with 4 ramification points, which is 2G plus 2, with G equals 1. So that's why it's hyperelliptic. Yes, correct. That's what you say is correct. By the way, the law. Okay, sure.
Okay, I mean,
Sir.
no, asking whether, there is this, how kind of theta duality where you can try to have spin close, another orthogonal sitting inside a larger spin, and you try to decompose this representation.
In terms of, I haven't thought about it.
Like GLN plus symmetry.
Interesting.
Canonically, so there must be a way of
Yeah, there is this finite group.
taking some other space and be able to.
Very interesting. Can have the symmetric group along with the Zima two things.
But here, getting another orthogonal group and spin group sitting inside a larger spin group, and then you decompose the spin group.
Decompose it as
Terms of
I haven't thought about it. Good. Yeah, it is.
So let's thank the speaker once again.
Okay.
the gift award.
Gift. You should not ask what is the gift.
As one of the speakers in the conference and also an interested participant, I'd like to thank the organizers for doing a fantastic job. enjoyed ourselves thoroughly. Yeah, so is it audible? Okay. So you, Professor Srinivas, for thanking us. So we are very much appreciate your kind of kindness and for coming a long way, all the speakers. So on behalf of the organizers, I thank all the speakers and all the participants for coming to this very compact and I would say one of the best conferences we have in the last 7-8 years. First conference we had in the last 7-8 years. Okay. Other than the speakers and the participants, I must behalf of the organizers, we also thank all the student volunteers. So Prakash Chandra Joshi wrote all the things about Kapil on the website and the brochure. Sandeep Das took care of the cultural event and took photographs throughout all the lectures.
Yeah, that's what we wanted to. This
Shiva Varman gave significant technical support to stream online. Tathagata, Vaishnav and Ayush Khare took care of the local hospitality. Mahima, Subrat and Prakash marked registration. And Kanad and Sandeep maintained all the logistics. Now there is one more student who I don't consider as our volunteer, but he is essentially our co-organizer, Dipankar. So on behalf of because Dipankar essentially depute all these volunteers and I think he and his team has done a fantastic work. Yeah. Okay. Okay. So now, as you know that these days in Hollywood movies or even in Bollywood movies, there are post credits. So after a powerhouse movie, there are name, and credits. And then there is a post credit, which is sort of teaser for a future edition. Now we also have a post credit here, which is that Upendra Prasad is turning 65 in 2 days. And today is Kapil's birthday. So the students have organized 2 cakes for both of them. And the post credit is a joint birthday conference of Dipendra and Kapil, maybe on 70th birthday. So thank you. Students, please take care. Okay. Okay, so let's have the cake cutting and happy ending.